somebody watching? Oh, wait a few seconds. Let me run it. Let me also start by thanking the organizers of this symposium and for giving me the possibility of being here. Here. Hello? Yes? And I'm going to talk about some kind of construction of a field theory that wants to incorporate capture some stringy effects and a theory of quark particles aspects related to the pattern of the extended objects. This is what I've been doing during some time, and now I'm collaborating with this people here, Eduardo Andres, Martin Maria, and Lucina Cabrera. So we all know this kind of picture when we have strings, and we look at strings at low energy. They look like all particles. So the string here at low energy look at the field theory. When we compactify a manifold, for instance, 4 dimensions, what we obtain is a quantification at low energies. And let me stress that even for a given topology, for instance, if we compactify the torus, we can have different gauge fields, different gauge groups for different moduli points and distance, for different values of the metric and axisymmetric difference. Parameters that characterize the compact torus lead to different gauge field theories. So the aim is to build up targets as space-time field theory that incorporates this string information. That means the gauge groups, non-Abelian gauge groups that appear in string theory, the non-Abelianities related parts of the fact that there are windings, that possibilities that strings winds around cycles. So this is a stringy effect that doesn't happen in point particle theory. And we want also to interpolate among these different gauge fields. It's not that we have just one effective theory for a gauge group, but we want to have an action that is able to describe all these different gauge theories. So this will be a truncated action, etc. But we want to capture some of these effects. And once we have this action, we would like to look at the variances, particularly for specific point, these invariances should contain gauge transformation, gauge field theory. And well, I know that many people are not familiar with these things, but in general, and we will deal with toroidal compactifications of electronics. So the picture is in string theory, something like that. You have a compactification, let's say the torus. Generically, the group is if we compactify for r dimensions. The generic group is an Abelian group, is U1 plus 16, 16,000 degrees of freedom. But when we move, what we change is moduli, we encode them in this 5 point, moduli the internal values of the metric tensor line. The picture is the following. We have a generic U1, when we move, vary these values, and we go to some non-Abelian gauge group, and we move again U1, we go to another Abelian gauge group, etc. This is the picture of the string theory compactified some art compact dimensions. So now this is what we want to capture with this action. A book example is if you want to bosonic string compactify it on a circle, the gauge group is C1 plus C1, but at a given point of the circle, the compact circle, that means a specific radius of the circle, this is called the circular radius. There are two vector multiples that become masses and vectors. So another two, two that become masses. So you have a finally this two processes. There is an enhancement, and this is due to the fact that there are windings such string effects. This is just some notation. When we compactify with Caruso line nodes and we have winding nodes, these are encoded into capital J. Just don't need to do that in detail. This is the model points characterize the internal values of metric and isometric tensor and lines here. And this information can be captured by a vector. It has a left part and a right part. This vector gives as a Lorentzian metric, and satisfies this property theory, and this means that the vector belongs to this so-called alignment. So with this, we can characterize our compactification. We look at the masses of the space. The masses are given in terms of the left and the right components of the spectrum, and these are the number of oscillators. So we see that the massless state, all the states are collapsed. The left mass is the right mass. A massless state must have n bar, which is here. No, those are the oscillators, one fermion. This is some number of constant. So this n bar must be 0 in order to have mass equal to 0. And m left equal to 0 means for n equal to 1, so n left equal to 0, or n equal to 0, and then left square equal to 2. These are the conditions to have space. The last impression is just to show that this expression of momenta, left and right momenta in terms of winding and momenta, and values of the whole, right? It's what we are not going into details. Just to give an example, we can look at vector multiples, vector fields in string theory. There are two kinds of vectors. Those that come from Caruso-like reductions of the eigenmodes, and those that appear due to the fact that there are windings. Theory, not going to details, but the first kind of vectors have they are all associated in string theory to vertex operators. This is the vector of a vertex operator or some vector is here in the mu. And these are the polarization vectors, but we write that them in terms of the space-time field dimensions, and this is also another vector of the right movements. And since it has n equal to 0 and n equal to 1, here there are oscillators, this vector vertices describe massless vector states when it's 0. This is what I try to show the transparency. And so this is one of the possible vector multiplets. The other one is the other massless state case. Again, there are massive, generically massive vector multiplets, and they become massless when LR is equal to 0 and L squared is equal to 2. Here, these are the cases of massless states that I mentioned before. So this is just to say that there are this equation L squared equal to 2 here, can be solved at some points in modular space for some values, specific values of momentum and point. So at some point, some given set of momentum winding needs extra massless vectors. So at that point, this group becomes constant. So we have a gauge group which is bigger than other points, points. So the group is enhanced to, instead you have it U1 to VR, we would have a sum group which has the number of vector multiples that become massless plus rank. This is the gauge group. This happens for the vector fields with this, but also for other fields. So scalars also suffer the same kind of have the same kind of behavior, and these are the vertex operators associated with this here. These are just some specific set of fields in string theory that for some specific values of momentum winding have become massless. Because this is just a subset of the things that appear in string theory. So this is just a very introduction to the logic spectrum fields. In general, we will have, looking at the polarizations of different vertex operators, we will have some polarizations. We have this n cases that have many Lorentz indices and many internal indices. We are now concentrated on a vector or some scalars with just one index. Sorry, the light is very close to the. And we have this momentum and unwindings and on left and right vectors, and we have for each of these vectors a conjugate coordinate. So we are going to consider fields that are functions of space-time coordinates and functions of this internal generalized coordinate that contains both the left and the right coordinate. So it's a kind of independent, not just an internal coordinate by a double coordinate. So we consider now, as an example, a Fourier expansion of these fields simply are periodic coordinates. We are compactifying some torus. We expand this field, and these modes correspond to the polarization. This is the proposal. These modes correspond to the polarization that we should write for the vertex operators of the string. So this is a Fourier expansion, but it has a limitation. The expansion is done over left and right momenta satisfying the right lattice. So once we have these fields, we concentrate just on the fields I mentioned before. We would like to touch an action, and an action in 3 dimensions, but in 4 dimensions, in terms of these fields. For the different, if we were going to include all the fields that appear in string theories, would be infinite number or possible spins, etc. Now we concentrate just on the subset. How to find the action? Well, we will find it at 3 level by comparing effective action with the result of computing scattering averages of 3 points in string theory. So we propose this action. Oh. things. Sit down.
Can you come like really close to the mic?
Okay. Now? Yes? No. On.
No, it's always right. It's all right.
It's all right. Now, yes? Yes, or so. Well, I'll try to. So this is the effective action that we are proposing. This is an action which is a function of fields of this kind. I mean, depend on the generalized coordinate y. Why this action? Well, as I mentioned, this is computed by comparing with scattering, three-level scattering amplitudes in string theory. I'm going to that. This looks like the effective action low energy for the heterotic string in the bosonic sector, but it has some differences, many. This that look like a field strength are actually similar to a field strength in the gauge theory, but instead of commutators of the fields, we have some star product. I'm going to talk about this. We also mentioned that these fields here are functions of y, and y, if we expand on y, has all the possible modes. So there are massless and massive modes in this expression. So the action reduces to the heterotic string action for low energies in 10 dimensions, contains this product which is commutative and non-commutative depending on the number of oscillators. I will try to explain it by time. It is read from the scattering amplitudes of a string theory at tree level. It contains masses and massive states, and it will just when we sit at some fixed point, at some modulate point, specific modulate point, it reduces to the gauge field theory of a given gauge loop at that point. So it reproduces. Well, just 2 seconds to say where is the origin of this. There's something missing in the PDF. We do a product of 2 Fourier expansions, but there is a here. It depends on the first stage and the second stage. What Caruso Klein momentum of this times the winding of this, and this is what leads to the non-commutativity of the product, was discussed by people in double field theory and also from some reason. All the reference are found, I don't know what. And this product is associated. Just a few examples. For instance, this object, which is a function of the generalized coordinates, when we expand it or look at the nodes, it has this form. This is valid for all the possible modes allowed for it to be in the right lattice. So these are massless and massless nodes. There are some factors here, some coefficients here that look like structure constants. In fact, when we look at massless states, or look at values of the momentum that lead to massless states, then this becomes the strength of the gauge. And this happens. We go to some fixed point, then to another model point, to another model point. So this is describing the massless gauge field strength for all these points. Same thing happens with this type of covariant derivatives. This is also kind of covariant derivative because there is a star product here. When we expand into nodes, this looks like similar to what we would have obtained in a gauge field theory. And this, in fact, becomes the coefficients
coming out.
I'm having this here. Yeah. Well, but the last transparency. So so I'm saying this describes not only the covariant derivative of massless states, but also able to describe the covariant derivative of massive states, as well as soon as we restrict to states that come from string theory states up to 0 or 1 or 0 number. So we'll skip this, even if it is captures also how the vector bosons get massive. But well, if you are interested, we can discuss later. This is just an example, an illustration. If we compactify on a 2 torus, we have a moduli points, two moduli points, this one or this one, that lead to enhancement to SU2 plus SU2 or SU3. This can be computed. So there are 6 vector multiples here that become massless, or 4 vector multiples here that become massless. So the SU3 examples and the values of the left and right momenta in terms of windings and momenta are given here. And we see that there are here 8 values, well, 6 plus 2 of the cartans that lead to the adjoint representation of SU3. So fields are living as adjoint representation to the vector fields. But there are also states here leading to the 6-dimensional representation, the symmetric representation of SU3. 3 times 4 divided by 2. This is a massive representation. So it has mass of the order of string scale. And the construction leads to the right expression for instance, the covariant derivative. We would write down the covariant derivative from the node expansion, the non-commutative product, etc. We have this expression here. And we restrict to the values given here, left and right momenta. We find some factors here, and these factors are just correspond to just the elements of the matrices that represent the generators in the representation 6. Yeah. So these are the matrices and the coefficients. I will compute the coefficients here. These are just these coefficients here. So we are being able to reproduce with a field theory, even cases which are massive, not only. It's not a low energy effect reaction. Of course, it's 0 minutes. So just to finish, I'm not going through all of this. It's just two transparencies, but once we have the action, we would like to look at the transformations that lead this action invariant. So we have 2 parameters here associated to transformations of the vectors with cartan index and the vectors which have no cartan. So these are the 2 vectors, the parameters that appear here. Also, when we expand them and compare the nodes, these give us invariances of the action, and they look quite similar to what we would have expected in a gauge theory. And if a field transforms like this in a gauge theory, the covariant derivative must recognize the field. And this is what we are finding here, using this non-commutative product, etc. And this is done at all points in moduli spaces. This is these are functions of the generic generalized variable Y. So sorry for hurrying at the end, and that doesn't work very properly. So now I'm going to, was just a summary, and just want to thank you, and also happy birthday to the Institute and to the ICTP.
We have time for the question.
It seems like that this effective theory is sort of a double theory. Double theory.
Yes, it's not a double theory, but it's inspiring to double theory. The variable Y generalized formula Y as a usual coordinate. Five of that.
Thank you.
Talking about some work done with Costas Kenderis and then with Matthias Neubert, specifically about holographic cosmology, and two issues there: one monopole problem related to these papers, and then non-gaussianities. So, after giving an introduction and letting you know what holographic cosmology is, I'll consider the general puzzles of hot Big Bang cosmology, pre-inflation, and how they are solved in holographic cosmology. And in particular, I'll focus on the monopole problem, for which we have a very specific quantum field theory calculation. And then the other issue, the monopole non-gaussianities, again, I'll consider the quantum field theory calculation. And I'll conclude. All right, so inflation by now is considered kind of a standard model of cosmology. It agrees with data, it solves a set of classic puzzles. It seems to do beautifully for everything. But I want to tell you that there is an extension of it into the strong gravity domain. So inflation and all of these things are usually for weak gravity. So this is an extension into the strong gravity domain. And being strong gravity, we can deal with it holographically by the SCFT. That is known as holographic cosmology. The specific model was started by McFadden and Skenderis with a phenomenological setup for the quantum field theory. So one uses a 2+1 dimensional theory with, let's say, is the so-called generalized conformal structure, and then fixes the parameters phenomenologically from fixing the CMPR data. I'll tell you that the parametrical fitting to the standard lambda CDM compared to the standard lambda CDM plus inflation is different, and yet the fit is as good. So they are indistinct, and they could be improved by lattice calculations. We'll also see that the classic puzzles of hot Big Bang cosmology are also solved in holographic cosmology. In particular, one of these puzzles, the monopole problem, we will need to do some detailed calculation in a toy model, but everything works as well. The correlators in cosmology come from boundary correlators in quantum field theory via a map defined by Maldacena that it's only extended to non-de Sitter, so non-ideal backgrounds. And in particular, monopole non-gaussianities will come from three-point function of currents. All right, so what is this holographic cosmology of McFadden and Skenderis? Well, we take the cosmology, the usual cosmology, and we kind of Vic rotate time into a spatial coordinate set. It's actually not quite a Vic rotation, it's more of a correspondence in cosmology and domain walls, meaning corresponding solutions. Just Vic rotate, there are some issues with that. And then we have fluctuations in the metric and fluctuations in the scalar field, just like usual cosmology is inflation. And because of this weak rotation, we also have to weak rotate momenta and also the Newton constant square. And this will have a gravity dual that is phenomenological. Now, when considering this, it also means that supposedly I weak rotate the n of SUM. That doesn't seem odd, but what I really mean is I do the calculation until the end, and at the very end I weak rotate n, as if it's just a parameter. I don't literally mean, you know, SU imaginary gauge. I don't mean that. I just mean do the calculation at the very end. Okay. So what do we do when we observe CMBR data? Well, we have the polar spectrum of scalar and circlets. So we have correlation functions of the metric and scalar fluctuations, 2-point functions in particular, and rescaled by some power of momenta gives this power spectrum. Inflation really means a scale factor that grows exponentially. I mean, standard of the exponential inflation. And so our correspondence, this would mean an A that grows exponentially as well. So this would be approximately the zeta, the case that was treated by Aldazabal by some kind of big rotation on the zeta. I'll not explain that. And he came up then from the big rotation of the usual ADS-CFT prescription, which is partition function equal partition function, came up with a prescription partition function in CFT equal to wave function of the universe in gravity. And then in 3 dimensions, these things are sources, whereas for the wave function of the universe, as usual, one makes the path integral up to a surface with 3 metric h, I, j, and scalar phi. But then, so this was Aldazabal, but then people have extended that to non-conformal theories and correspondingly non-de Sitter exponential, non-de Sitter A of Z. This was done in works by Spenderis. Moreover, we also assume that just like for usual ADS-CFT, which was defined in the case of classical perturbative gravity, but then assumed to hold for all couplings, also assume here that this is valid at any coupling, including the case we're mostly interested in, the strong non-perturbative gravity. So then, we have a new kind of model where the CMBR perturbations are generated during a strong gravity phase that usually, with usual methods, would not be calculable, but now it's calculable via ADS-CFT from perturbative quantum theory. Then a holographic, meaning strong gravity map to perturbative field theory calculation, gives the following map. So this was calculated by Spenderis and Papadimitriou first directly, just without any assumptions. But then it's also derivable by this Aldazabal map. We did this explicitly in the paper, but it was kind of clear. So the mapping is, roughly speaking, the power spectrum of Hij and Phi fluctuations goes like 1 over the power spectrum of the energy momentum tensor. I mean, this is a tensor, so what you really do is expand in some tensor structures, and then only these scalars are inverted and imagine part and so on. But roughly speaking. Okay, then what about the set of phenomenological quantum field theories? Well, they are super renormalizable and have this property of generalized conformal structure. which means that dimensions are contained only in the momentum and only via this effective coupling. In 3 dimension, G squared n has dimension 1, so you have to divide by Q to get dimensionless thing. So one simple way of thinking about it is that if you would take a 4-dimensional conformal field theory and dimension reduce to 3 dimensions, you would get a theory that has generalized conformal structure. Generalized conformal structure is more general than this case, but this is a particular case. So, so this is the general theory that we're talking about. So now the power, the momentum appears via this G squared diagonals. And then you calculate in field theory, and you find that these A's and B's, which give you the energy momentum density 2-point function, they are some expansion in the effective coupling. Usual quantum theory expansion. This is a 2-loop calculation. So then, via this holomorphic, this holographic map, we find this this thing that the power spectra, scalar and tensor power spectra, are 1 over something plus log Q. So now let's understand, this is a question that I get a lot. Why is the spectrum almost flat like for inflation? Well, the reason is this generalized conformal structure. If you would say conformal, you would mean independent of momentum, right? So this generalized conformal structure is the basis of why the spectrum is almost flat like for inflation. So the quantum duration appeared only in this G squared n over Q, and this GF squared F effective is small. So how about the comparison to lambda CM for inflation, the usual CMVR fit? The usual CMVR fit is like this. You write Q momentum to a power ns minus 1 that's very small, plus some even smaller thing. But you note that this then can be expanded in principle, and you just write 1 minus small times log Q, which is also the same as 1 over 1 plus small times log Q, right? So if you would just, you know, at a very rough order, it's no surprise that these two different functional forms are kind of the same. What is surprising is that the data is sufficiently complex that it could distinguish between these two functional forms, and yet it doesn't, right? So the data is as good for lambda CDM of inflation as for holographic cosmology. Specifically, you see the chi-squareds in here, which are 0.5 away from each other, which means that they are indistinguishable. Moreover, in order to get this fit, you have to only consider the region where G squared F is perturbative, because you did a dual calculation. So you have to subtract some part in the CMVR data, and to put it back in, you would need to go to lattice calculation to improve this. And there's a bunch of people in the UK doing that for a while, but they haven't yet achieved this. I'm sorry?
Is there a scalar field in the boundary?
Is this what you call?
Is there a scalar field in the boundary corresponding?
Yeah, that's what I said. So in the bulk, we have metric and the scalar field, right? So this is the
electron normally.
So this is the usual thing. So cosmology is always kind of 3-dimensional gravity plus a scalar field. That's no different. Okay. I mean, inflation, if you want, but most cosmologies that work are reducible to this, to 3-dimensional metric plus a scalar field.
That's scalar field.
Right. Yeah. Okay. Another quantity that we need in this case is a global symmetry current with its correlators that are similar to the energy momentum tensor correlators. They are some tensor structure times the scalar function of the effective coupling. However, if you talk about the global symmetry, then you have to specify your theory. You cannot just say anymore you're in the phenomenological theory, because that is phenomenological, has general parameters. So you need some sort of global symmetry, and You need therefore to restrict the model. But if you do that, this thing will be related to monopole perturbations. So why monopole perturbations? Well, the other thing that inflation does very well is address a bunch of problems that were there before inflation, and if you want to remove inflation, are still there. One of them is the smoothness and horizon problem, which is, you look at the sky, you see correlations at all angles. But the things that, without inflation, the things that with normal cosmology are actually correlated are just this very small angle on the sky. So if you do the calculation, you see that there's about 72 horizons in the sky. And yet, there's not. They're all correlated. Right? So how does inflation solve this? Well, during inflation scales that were inside the horizon, so initially correlated, get outside the horizon, and then get back inside during normal cosmology. That's how it works. In holographic cosmology, it's something more interesting. One starts with the observation that inverse RG flow in quantum field theory is mapped to time evolution, so cosmological time going forward. So then, in principle, you have a singularity at time 0 that's mapped to an infrared singularity in quantum field theory. But there was a conjecture in the 70s by people from Yale that I forget, and then it was proved a couple of years ago by Spenderis et al. That there is no IR singularities in these quantum field theories. And so that means that really, by the map, there is no cosmological singularity at all in cosmology. And that also means that there are correlations at all scales. How about the flatness problem? The flatness problem can be reduced to saying that the omega minus 1, the deviation from flatness, grows like this. And in normal cosmology, p is less than 1. So omega is much closer to 1 in the past. Inflation fixes that by having exponential expansion, so omega goes towards 1 in the inflation, and then goes away from 1 during normal cosmology. In holographic cosmology, this is mapped to the fact that the dt correlation function, energy moment tensor, has an anomalous dimension, q to the 3 plus 2 delta, and delta is generated positive, which is a way of saying that t is marginally relevant in 3 dimensions. And that means that the perturbations in t are diluted in time. And if you remember that inverse RG flow is dual to time evolution, that means that the perturbations are diluted into uv, corresponds to perturbations being diluted in time. There's also the entropy problem. Why is the entropy so large? In inflation, you have the exponential expansion that increases the entropy inside the horizon. In holographic cosmology, there's just the general quantum field theory statement that degrees of freedom, the number of degrees of freedom increases along inverse RG flow, meaning along future time. So that defines the error of that. But finally, the one thing that I want to define is the monopole problem, which is the hardest to calculate. So in this case, I want to say that the monopole in the bulk is dual to vortex in the quantum field theory. And as I said, I need a global symmetry, so I need to fix the action. I need this toy model with some symmetry, some SO3 symmetry, and some SO3 global currents. But in a paper with another student of mine, we've proven that the calculations are valid for almost all models, not just for this toy model. And then we calculate the 2-point function, and you see again that the dimension is positive, so the current is irrelevant, grows in UV. That's the other way around. However, I need the vortex current, not another current. Since I also know that the general form of this 2-point function, because of these people, is supposed to be like this. So there's one scalar function t, and basically when going between another current and the vortex current, I just invert this scalar function, which means basically I just invert the sign of the anomalous dimension. So J is irrelevant, J tilde is relevant, so it decreases in UV, decreases at wave time. So it's solved. And then monopole non-gaussianity. This is work with Matthias Neubert last year in a couple of papers. So first, the 2-point function in gauge fields. This is, as I said, like in the case of the energy momentum tensor, this is roughly like 1 over the 2-point function of currents. And then this is like the directly proportional to the 2-point function of vortex current, not other currents. So that in particular means what I just said was correct. So if this thing decreases in the UV, then the monopole correlation also decreases in the UV. And we also can calculate what happens to the 3-point function using nothing but Aldasena's map and the usual way to insert the wave function of universal correlators. And we find that the 3-point function of gauge fields is reducible to the 3-point function of currents, and something similar for the 3-point function of metric versus energy momentum tensor. And for some kind of forward type of momenta, which is something usually considered for non-gaussianities, then we reduce the 3-point function of currents to 2-point function of currents by this kind of formula. So we can calculate the monopole non-gaussianity from just the 2-point function. So it's similar to what happens to usual non-gaussianity of metric and scalar. So to conclude, holographic cosmology matches the CMDR data as well as inflation. It is a continuation of inflation into the strongly coupled regime. It fixes the problems with Big Bang slightly better in slightly better ways than inflation. And we can calculate any endpoint function. I showed you 2- and 3-point function, but any in principle, including non-gaussianity in CMDR and Monopole distribution.
Thank you for all the questions.
Maybe the supergravity takes over these
Okay, you reached the okay, very good. So the reheating is the one thing that is not entirely defined. So it's a very important point. Yes, I agree. I've written a preliminary paper on how it could be possible to define reheating in this model, but it is crucially important because you see during this non-geometric phase, the strong gravity phase, the sort of gravity becomes stronger and stronger as time evolves, but then it has to grow weaker and weaker as in usual cosmology. So this transition is defined by reheating, and I've written a sort of a paper describing the general kind of model, but I haven't been able to pin it down to work everything out in a concrete model yet. So, but myself and also Costas Skanderis is doing that. We're aware of this, and it's happening.
It's a very naive question. Do you have any analog of the bunch days from?
No, you see that this is much more than that. I said, I emphasized it that because of this theorem by proof, projection by in the 70s and proven now, infrared singularity is not there. So it means there's no cosmological singularity, so it's completely well defined. There's no arbitrariness anymore. There's no, it's completely defined. So much Davis vacuum is a choice to choose something else. Here no, is there? Okay, that's good. I would think that just okay.
Just I feel a lot of white.
Well, yeah, this is you know, the usual thing. You can calculate this, so you do. I mean, we haven't seen non-gaussianity even in usual scalar field, in the metric and scalar. that would be a big deal to calculate the 3-point, to observe the 3-point function. So that would be first. And then also we haven't seen monopoles yet. So we can, the 2-point function, so to say, right? The 3-point function is even smaller. So yeah, absolutely. It's just for the moment, it's just to show that it can be done.
Okay, thank you, Horatiu, good afternoon. So this is a shift topics, more phenomenological particle physics, and I'm going to talk about the possibility of testing physics to understand a model in non-local momentum dependent effects in Higgs couplings. This is work done in collaboration with the student Pedro Vieira, and ongoing collaboration with him and Gustavo Burdman. Birthday, etc. So I think it's a short talk, so I don't need an outline to proceed. So the idea is the following: we're going in particle physics to have a transition between the energy to the precision measurements, particularly in the Higgs sector. Okay. So if we are going to look for physics to understand a model, the energy frontier is still going to be there for a while. And so, although we would still look for new physics, low energy effects like dark sector, dark matter, etc., the important point would be precision tests, not just low energies like spectral physics or electronic physics, but specifically in the newest sector we have discovered, which is the Higgs sector. And in particular, Higgs couplings to everything, precision, increasing precision, particularly in the highly massive HC, is the name of the game for the foreseeable future. Okay. Now the standard approach to study the electric sector in general, but in particular now the precision, increasing precision, the Higgs sector, is the effective field theory approach. So the new physics here is encoded in an expansion in local higher dimensional operators like this here. Dimension 4 standard model, and there are higher dimensional operators, and there are several originally several ways to do this. The standard model effective field theory, the Higgs effective field theory. More recently, you can see this very nice overview by Oscar and Matthias, and Oscar is going to talk about this in a couple of talks. So I'm not going to, no, maybe not. Okay, but ask Oscar anything about effective field theories. This approach is totally independent. But of course, it requires a large number of operators in principle to have a fully modeled independent approach, 59 operators for dimension 6. The question that also is it enough to go to dimension 6? Is there any need for dimension 8 operators? And the question is, what if there are non-local effects, such as momentum dependence decouplings, that are not necessarily easy to separate in the standard theory approach with the dimension 6 operators? How would we go about to see this from the data we're going to have? It's a practical question. Of course, that effective field theories always can account for this effect. The question is how many operators do we need, and that in order to stick to the model independent approach. Now, another way to do this is to have a model-dependent approach that will allow you to compute non-local effects in the Higgs coupling to standard particles, would be H bosons, would be the top mostly. This typically, as we'll see in a minute, will require that either the Higgs or the standard particles, one of them at least, should be off-shelf. In a minute. And so this will define some sort of momentum independence, non-local effect through something that we could call the form factor of the Higgs couplings. And so some people have proposed looking at these kinds of non-local effects as the form factor, so we could complement the EFT approach in a more model-dependent, but more phenomenologically easier to compare with data. Okay? So this is sort of the idea of this form factor model-dependent approach. It computes with form factor either in a specific model or something that is quite almost a model. It gives you the full non-local dependence. You could match with the EFT if you want. You lose generality, but you gain the power of constraining those particular models with the power of all the data you have. In general, you have a Higgs coupling to a standard particle X, which in some extension of the standard model will have some form. It will be a momentum dependence, two dependent momenta Q and P. There is the value of the standard model of this coupling, and there is this factor kappa, which is a normalization that if you use this normalization for the momentum dependent form factor, but it can be shown that if you use the form factor at on shell, for example, for the Higgs momentum, then essentially this object here, which is a shift in the actual value, this coupling can be absorbed, can be reabsorbed as long as you stay on shell. So in order to actually see these effects, you really need to go off shell to really observe this momentum dependence. It's not just something that you can do in a specific momentum, because you can always reabsorb that shift. Okay? So you need to have off shelness. And let me give you an example, specific example of what I mean by off shell. So this is the following process. Is a proton-proton going to Higgs, which I'm going to assume is non-gaussian mass shell, going to a couple of Z bosons, which could not be on shell, but it is advantageous because the rate of this off-shell Higgs will be much bigger when the Z's are on shell. And this is decay on shell on 4 electrons. Okay. Now, here at the standard model diagram, there is this dominated type Higgs production type with the top triangle. There is this box diagram which has no Higgs. It's also very big. And then you can add these dimension 6 operators, these two in particular, this one affecting the triangle diagram with this coefficient Cy, which is 0 in the standard model, and this coefficient Cg affects the coupling, the effective coupling of the gluons to the Higgs. So in principle, you can do this analysis. These couplings are small compared to 1. If you use some cutoff in this dimension, higher dimension operator expansion, then essentially these coefficients are order of the grid scale over some cutoff square. So now the question is, when you produce, if you're just looking at the Higgs production on shell, if the Higgs was on shell, then it turns out that the Higgs production from gluon fusion is proportional to the sum of these coefficients, where this coefficient Ct is just 1 from the standard model, and then there is a minus this Cy, the real part of the Cy. Okay, so essentially there is a degeneracy in the Higgs production on-shell Higgs production in the standard in this coefficients for dimension 6 operators. And this degeneracy, this is the direction Ct plus Cg by the square. And so, how do you break this degeneracy? Now, this you can see this from the fact that on shell you have the mass of the Higgs, assuming it's considerably smaller than the mass of the top. You can integrate the top quarks, and then integrate out the top quarks. Basically, you have all the same operators in here. And so this degeneracy appears as the sum of these coefficients being essentially 1 coefficient effective. So you need the Higgs to have a momentum much higher than its mass, much higher than the top mass, in order to actually break this degeneracy. So when you actually, so how do you break the degeneracy? You can either go to TTH, which has is testing the top coupling of the Higgs directly. You know, there is a top anti-top with one of them spitting out the Higgs, or you can use this off-shell process I just mentioned for very large MZZ or center mass partonic moment energy. And so you see, it's also important point that there's a huge cancellation between the triangle and the box for the aficionados. There's a huge cancellation between these two because of unitarity, right? If you cut in the top lines TT bar going to CC without the Higgs violates unitarity at some energy. The Higgs diagram stores unitarity. So even if the tops are off shell, these two diagrams have large cancellation. And that's important because if you upset the cancellation with new physics, this will have a huge, enormous effect in the data. And so, for example, so here there's a large cancellation. The off-shell large center mass energy is dominated by real longitudinal Cs. The radian is mostly transverse Cs. And here is the cancellation between the longitudinal Cs, the triangle, and the box. You can see that if they go more or less the same at high energies, then there's a difference energy dependence, energy score dependence for the blue Higgs dimension 6 operator, and you can see what's the differential power from using this. This is from this paper. Between this is C in day notation they use kappa bar. This is our CT, and so the triangle dimension 6 operator plus the standard model and the gluon dimension 6 operator. This does much discrimination. 3 inverse counterparts at the high luminosity C will give. So some discrimination is not I'm sorry, it's not a 45. Oh, okay. Spoiler alert. It's some discrimination, but it's not great. This is as good as the it's going to do by the time we're all retired. Okay. So and this is assuming that there is no contamination from dimension 8 operator. Now, and that's if on the other hand you just take a completely model-dependent approach, you have a lot more power. The data will have a lot more constraining power from the models, so that you just essentially scan over different models that will be momentum dependent. And so if you go off shell, then you can constrain this coefficient CT. Momentum is not mx squared, much better. So in this paper, we did examples that are well known, so as to get a handle of what it is that we're going to do the phenomenology. So we use the composite Higgs model that is very well understood, where they integrate out fermion and vector resonances to get the momentum dependence, so you know where everything should be. So basically, you say, well, you can just go and catch the resonances, although you cannot see it's not that energy now. So you should see this before the resonances. And then you can have weird mixes with heavy scalars or an antiparticle sector, which is my favorite since it's there are no, it's not my favorite model, but it's my favorite here because it's a quasi-conformal high energy theory where there are no resonances. So this is how you see the differences first. So you can do these things. I'm not going to go through the idea because I just told you, you integrate out particles in this minimal composite Higgs model. And so you have to make sure you're not screwing up the data you have. For example, Higgs production has to be accounted for correctly, et cetera. But this tells you, for example, that the new physics scale has to be bigger than 1.5 TeV, which is also already a bound that's better than what we needed before of this model, which was 750. And then in any case, here are the possible effects in the TTH cross-section normalized by the standard model cross-section, and the CH associated production also normalized by the standard model. Here is a lot of model dependence. These are couplings choices that give you large effects within the bound that's allowed. In the case of the associated production, it is gauge couplings, so it's more constrained by gauge invariance, and you see the effects, the deviations from the standard model, which is the one line, are smaller, but you can see already that it is possible to have deviations from this dash line, which is the predictions of a non-momentum dependence of the coupling, just from having a cosine suppression of the couplings. And that is sort of going to be different. Now, when you go to the data, you see, you know, how the question is to simulate this correctly and see how much luminosity you need to see these kinds of effects to 5 sigma, of course. That's the game we still haven't played, but that's part of the problem. additional scalar doublet is pretty boring. Let's go to the unparticle case. I like this case because, again, there is the spectral two-point function for an operator which is not a scalar particle. It has a dimension bigger than 1, smaller than 2. It mixes with the Higgs in a way that is dictated by gauge invariant, so it's very constrained. And then you'll see the effects here for the scalar, which is always an enhancement with respect to the standard model. But for example, if you look at PP going to A star to CC on shell for leptons, you see that in the particle case, when the form factor is an enhancement, you have some enhancement of the signal. But when the form factor has a suppression, you have a bigger enhancement. That's because the suppression is in the triangle diagram, and this upsets the cancellation box, so the box wins, and then you get more. So there is a discriminating power not just with respect to which coefficient of the EFT you have, but also with respect to what kinds of physics is actually producing this effect. So I think it's model dependent, but you know. So that's it. This is my last one. So what I want to say, this is what are we going to do in the future? This is a program to build allowed form factors and Higgs couplings and design tests that they have an energy LNC to match with complement the EFT approach. And so what are we going to do for that program to succeed? First, there are constraints on these form factors. Causality and unitarity are relatively easy to do, but we have to have constraints from analyticity. This is something that has to be very carefully done. There are interesting results in this that we have to consider for the actual form of the form factor. There are phenomenological bounds to the large form factors that have to be put in together with the theoretical bounds. These are predictions for the high density LHC. Using these properties, you can predict effect in new channels. If you go to Euclidean momenta, for instance, the Higgs, maybe you'll have in vector Boson fusion the T-channel Higgs in the Euclidean momentum. That is a prediction of the model that would, and the question is, can you see that effect in vector Boson fusion at the related to that last comment is what can these probes tell us about the Higgs sector and the hierarchy problem? Have you ever thought about the hierarchy problem technically? In fact, you also thought about effects for Euclidean momentum. Because in fact, all these calculations that we do has either the Higgs or some other particle coupled to the Higgs in Euclidean momentum. And so these form factors should be able to, we should be able to analytically continue them to Euclidean momentum in order to probe how the behavior of these form factors in that region of the complex plane for the form factor is, and if that prediction has anything to do, has the suppression needed to maybe have to do with the hierarchy problem. For the form factor suppression in the Euclidean, which is what it should be, is maybe related or a solution to the hierarchy problem. So that's it for me. I don't know if I okay. Question?
It's more a curiosity. I heard some time ago that the Higgs could be a bounce state. It's happening, or is it still not there, or is it completely out of the game?
No, I mean, I played that game for a long time myself, but I can only say that the scale of the compositeness of this system by now has to be at least 10 TeV. This is the scale of it. So the games we play, for example, in this minimal composite Higgs model, which is a composite model, is the game is that the Higgs is light compared to the 10 TeV because it's a pseudo-Nambu boson. So it's like a pi, right? So we separate the scale to 10 TeV. But then at 10 TeV, there is some new physics happening with maybe new fermions bounding, you know. I mean, it's not a bound state, it's more like it's not really a bound state, but it's a state made of positive fermions. Although there are some weird models that have supersymmetry and 3D-part bound states. But in principle, the game is still there, but the scale of compositeness has to be about 10 TeV roughly. 4 pi V. 4 pi, that's the electron scale, because otherwise we would have seen deviations in the couplings already. About
hierarchy.
I didn't really say enough for people that are not into it to explain, but in principle you can say that if the hierarchy problem, we typically think of it as the UV sensitivity of this. The only, let's say, in the Standard Model there is only one supernormalized operator, right? And that operator then is UV sensitive. The m square, 5 square operator is UV sensitive. And then you expect that with quantum corrections, maybe if this phi, this Higgs coupling with all the particles of the Standard Model is actually suppressed as you go to UV, to the UV, then the UV sensitivity is, so you're missing this suppression of this coupling, right? And so the Higgs usually, we think about the hierarchy problem as a loop correction, all the loop corrections of the Higgs, say the top, W itself, are quadratically sensitive to the UV. But if it turns out that there are suppressions of these couplings, then you may turn that quadratic UV sensitivity to maybe already, which is perfectly acceptable. So the question is, if those Euclidean momentum form factors are a suppression, which when you actually close the loop will give you a smaller UV sensitivity, or meaning instead of a square is a log, then you may say this is a hint that maybe these effects have something. That is, that's all.
Any other questions? If not, let's thank Gustavo for my favorite problems of axion-like.
Yes, thanks a lot. And it's a great pleasure to be here. And happy birthday, ICTP-SAIFR. I don't know if any of the officials is here. Obviously, they end tomorrow. So I hope this fits very nicely with Gustavo's talk, because this was searches for new physics in the form of heavy particles or heavy ion particles, and I will kind of go in the opposite direction. And I'd like to start with this picture, which shows kind of the phase space for new physics discoveries. What we see here is the mass of new states, particles beyond the Standard Model, and they are coupling to the particles of the Standard Model. And of course, before the LHC started data taking, basically because of the hierarchy problem and the Wick miracle, we expected to find relatively light, strongly coupled particles. This region is now excluded. So this is ruled out, and then you see there are basically 3 alternatives. We can keep pushing the mass scale to higher orders, and as Gustavo described, this is described by Standard Model effective field theory or by concrete models, of course, of physics. You can have very heavy particles with very small couplings. I will call this hopeless method. You can still describe it by Standard Model effective field theory, but just not find an effect because the effects are too small. And the other logical alternative is to look for extensions with light new particles, but very weakly coupled. So basically, we haven't seen new physics, not because the particles are so heavy, but because they're coupled very weakly. And a nice model of a very weakly coupled new physics particle is the axion. And it's well motivated because of the strong CP problem. So basically, the old Petri-Quinn solution is to add a new scalar field to the Standard Model. It couples to some kind of fermions charged under new symmetry, so-called Petri-Quinn symmetry. And you see that this scalar field can be written as a modulus and a phase. And basically, the A here in the phase is the axion. And F is called the axion decay constant. Then you break this Petri-Quinn symmetry dynamically, like in the Higgs mechanism, just same type of dynamic symmetry breaking. So there's a flat direction here. for the axion at the minimum, which means any value of the phase would be identical, and performing chiral transformations, because you have this coupling to chiral fermions, you can rotate this phase of the axion along with the theta term of QCD into this operator. And now QCD instantons generate a potential which essentially sets this term to zero. So that's the solution to the strong CP problem. Now, one critical feature of this axion is that its mass is automatically going to be very small because it's inversely proportional to this axion decay constant. You can see here that the axion mass squared times the decay constant squared is essentially the pion mass squared times the pion decay constant squared. So if this FA is very large, MA is very small. You can also show that the axion coupling to photons is inversely proportional to FA. So in other words, you find that the axion photon coupling is inversely proportional to the mass, and that gives rise to this yellow band for the QCD axion in the plane of mass versus coupling to the photon. There are some order 1 model dependencies here, so it's not a straight line. It's basically this kind of proportionality, and this is existing experiments. There's a lot of future experiments which would go closer to the axion band. However, there's many ways to relax this strict relation between the mass and the coupling of photons. And so more generally, one talks about axion-like particles, not strictly QCD axions. And one can think of them as pseudo-number bosons of spontaneously broken U1 symmetries beyond the standard model. Of course, such symmetries exist in a large class of extensions of the standard model, in particular, including the composite models that Gustavo described. So basically, we can have heavier axions than this yellow band would suggest, and if they are relatively heavy, so they enter, let's say, you see this plot, we go to very, very small masses. This is an MEV, so we go to small fractions of an MEV, of an electron volt. But if you push in the other direction, then particle physics experiments can be used for these axion-like particles. And I will give you basically two very different examples of how one can use particle physics experiments to do that. We need an effective Lagrangian for this axion-like particle. And the characteristic feature here, really, then I would call this an axion-like particle, is if it still has the property that all the couplings to the standard model are suppressed by 1 over f, which means really there are no renormalized interactions. All the interactions are of higher dimensional nature. And the reason is that you have to maintain this shift symmetry. So you see that the most the simplest coupling to fermions you can write down is that you take the chiral currents of the standard model and couple to a derivative of the axion. That's a dimension 5 interaction. Likewise, the coupling to the Higgs is a dimension 5 interaction, and the coupling to the gauge bosons is also of dimension 5. Now, this Lagrangian contains 5 unphysical parameters. There's simply redundancies that you have to take care of. And I will always work with physical combinations of these coupling parameters which are independent of these redundancies. Now, imagine you have a UV model that has such a conjugate symmetry and breaking mechanism at some relatively high energy scale. If you want to connect that to experiment, you have to do the usual effective field theory machinery. That means you have to start from this effective Lagrangian at the high scale. The high scale, like Gustavo mentioned, is 4 pi f, where it's the decay constant. And now you have to evolve it down to weak scale, then integrate out the weak scale particles in the standard model, and then with low energy physics, you even have to run down to yet lower energies. I will give you one example that lives at the weak scale, and one example that lives down at the sub-G scale. And, you know, the technical details of this running have been worked out years ago. So I'm going to give an example of Alp searches in Higgs physics. And I chose this because one of my experimental colleagues, after we had proposed that, he wanted an ERC plan to do the measurement, and they just published an Atlas paper on exactly that idea. And the motivation for this was the following. This is a plot that shows constraints on the coupling to photons, and most of the constraints here are from cosmology and astrophysics. So this is supernova constraints, cosmological constraints, astrophysical constraints, but also light shining through wall type of experiments. And then you see here LAP and LHC. So basically, this is the region where particle colliders come in, but you see that these constraints tend to be much weaker than the other ones. And there's this, there used to be this wide open space here where there were no constraints a couple of years ago. And this third channel Higgs decays to 2 Alps and then became 2 photons, 4 photons, allows you to basically probe this parameter space. Exclude almost all of the wide open space, and we did this analysis at the time, assuming 300 inverse femtobarn in the high luminosity run of the LHC. The analysis that I'm going to show you is done with 140 inverse femtobarn, so it's a factor of 2 weaker than what we estimated here. But other than that, basically, they find indeed that they can exclude all these regions here of our photon couplings, and you see that compared with previous analysis that were up here, they can do many orders of magnitude for exclusion. Photon coupling, and in particular, this includes this region marked here in red and marked here in yellow, where an axion-like particle could account for the anomalous magnetic moment of the muon, if you still believe that there is an issue with the anomalous magnetic moment. But basically, you see that this parameter space is excluded. So it's very peculiar that you can use Higgs bosons to search for these very light, very weak particles. The second example I want to mention are flavor probes. So some rare weak decays measured at B factories or K-on factories can also be used to constrain these particles. And I'm going to use a very low energy process, K minus, pi minus plus axion-like particle. And it's cute because you can actually use the chiral Lagrange to calculate this process. And what you find is that at leading order in the chiral Lagrange, there's these 6 diagrams that when we calculate, they account for alp-pion mixing, alp-beta mixing, but also a vertex graph where the alp somehow couples to the weak interactions of the standard model, and then initial and final state emissions, and finally a diagram where the alp interaction itself is the source of flavor breaking, which is also allowed. We analyzed this a couple of years ago and found to our surprise that actually, even though there's a long literature on this decay, it was not done correctly. The literature kind of was a mistake in the way this diagram was implemented in the chiral Lagrange, and that has an important implication about the factor 40 enhancement of the rates. And the interesting thing here is you get constraints on the flavor violating alp coupling from this diagram, but also the flavor conserving couplings, because what happens here is that the alp couples in the strong interaction with minors and k's, and then the weak interaction is simply that of the standard one. So what is this new flavor changing alp vertex? Basically, in the high energy theory, this comes about either because at the UV scale, the alp simply couples to downtime quarks in a flavor of diagonal way. There's a priori interaction. But you also get it through this RG evolution that I described, because we have to run from the high scale down to the low scale, and we have W bosons in the standard model, which of course have flavor of diagonal couplings. So even if this coupling is flavor diagonal, the flavor violation will come from the W loops, which of course we have to integrate out when we discuss K and pi physics. Are these effects important? Yes, actually there are. If you assume a decay constant of 1 TeV, so new physics scale typically 4 pi f, 10 TeV, let's say, then you find, and if you also assume minimal flavor violation, I will show you in a moment why this is a reasonable thing to do, then then you find that in the coupling to left-handed down quarks, you get these loop-induced effects from these two diagrams where you get the dependence on the parameters of the CKM matrix, and then the alt coupling to top quarks from this diagram, and the alt coupling to W's from this diagram. And then the two order, there's also a contribution involving the alt blue. So basically, this flavor changing vertex is there, even if it's absent at the ultraviolet scale, it's there because of arching. Now, there's other subtleties in this analysis, and in fact, we only found this in very recent work late last year. Namely, people usually, when you describe the weak interactions in the standard model, there's a single octet operator that gives the dominant effects. If you know the chiral Lagrangian, you know what this means. This is the lowest order operator. But actually, if you introduce an ALP, there's additional operators because an ALP acts like a theta source, and you have to implement this theta source with the chiral Lagrangian, and you can couple d mu theta to a left-handed current, which is basically this operator. So this is an operator which simply doesn't exist in the standard model, but it's there in the presence of an ALP. And there's another operator, the so-called weak mass term. It exists in the standard model, but it's a total derivative. So it has no observational consequences. But again, in the presence of an ALP, this is no longer true. And this operator also exists. The only thing that helps you is also, and I should say that we know the coupling of this operator from K to pi I phenomenology, but we don't know the couplings of these two operators. If you assume a flavor symmetry in the UV, such as minimal flavor violation, then the weak mass term, again, is unobservable. But this operator here is not unobservable, and it has an undetermined coupling. So there are some uncertainties. Also, at next to leading order in pi pt, which is the calculation we did in this paper, you have to construct the operator basis with 4 derivative terms. And also here, in addition to the many operators that exist in the standard model, you have to add QCD and weak interaction operators proportional to theta, which don't exist in the standard model. Which means that there's sensitivity to several poorly known low energy constants, but there's ways of estimating this, in particular, running the scale in this loop calculation. And then basically, there are now chiral loop corrections and higher order point-like vertices for the flavor changing ALP couplings and for the flavor conserving ALP couplings. And all in all, curiously, there's exactly 100 diagrams you need to calculate. And we did that. And this is the result, basically. So this is for the octet operator, which also exists in the standard model. This is the leading order result, and this is the next to leading order result. There's a term involving the Gluon coupling, the up quark coupling, and the down and strange quark couplings. And you see that the next to leading order corrections, they have large uncertainties because of these not well-known low energy constants, but you see that they tend to be quite a bit smaller than the leading order contribution. So in a way, the uncertainties are big, but the effect itself is reasonably suppressed. And I can also show this in pictures, even though maybe this is a bit hard to see. So this is as a function of the ALP mass, the contribution to the Gluon coupling at leading order. It's about 2 in these units. The next to leading order is very small on average, but with a large uncertainty. This is kind of the same picture for all the other functions. And then, as I mentioned, there is this other coupling that is presently unknown. Thankfully, it only contributes to one single coupling, only proportional to the Gluon coupling, but with an unknown overall coefficient. And I will show you the dependence on that coefficient in a couple of slides. We can now take these results and use the most recent NA62 experimental limit. They actually perform a search for K minus to K minus plus a light blue particle, which they call X. And of course, we haven't seen the signal, so there's an upper bound, and we can take this upper bound and translate it to bounds on the various couplings in the chiral Lagrangian. And I give you these bounds for 2 different values of the alt mass. And I plot the bounds, instead of plotting bounds on the couplings, I plot bounds on the ratio of F over the coupling, because that is essentially the new physics scale, the effective new physics scale that can be invoked. This measurement. And I give you this new physics scale in TeV. And the first thing you see from this table that we can probe multi-TeV new physics scales. So for instance, in the gluon coupling, we probe around 40 TeV. In the up quark coupling, about 2 TeV. The down quark coupling, about 10 TeV. So this is powerful. This is much better than one can do in other particle physics probes. You also see that we probe this off-diagonal coupling at the level of 10 to the 8 TeV, which is huge. 11 GeV. Okay. So actually, this scale is so high that one probably needs to assume a flavor symmetry. Because if there was no flavor symmetry, if this was just basically F times an order 1 number, that would correspond to 30 times 10 to the 10 GeV. And on the other hand, there are cosmological upper bounds on the alt decay constant, which, depending on the precise axion model, are in the range 10 to the 9 to 10 to the 10 GeV. So you see that this is an order of magnitude, or 2 orders of magnitude above this upper bound. This upper bound is under some assumptions, maybe that the G symmetry is broken after inflations. In principle, you can probably avoid it, but it's pretty generic. And you see that if you have this 1, 2 orders of magnitude fine-tuning here, it's better to assume that there is a flavor structure at the high energy in order to avoid this bound. So of course, the most radical flavor structure is to say it's completely flavor universal in the UV. And the question is, do you still get interesting bounds in that case? The answer is yes, because of these diagrams I mentioned earlier, because through the running to low energies, we induce the flavor change nonetheless. And in this model now, flavor universal out at the high scale 4 pi f equal lambda. You see that at the high scale now, you get these bounds. You probe the gluon coupling in the range between 50 and 100 TeV, and you probe the coupling to the up sector. That is from the top coupling, but now if it's very universal, I just call it the up sector coupling. It's still constrained at the level of 2000 to 4000 TeV. So even in this model, we get these very, very strong bounds on almost all coupling. Gluon, W, down quark up. The only thing that's not constrained is coupling. So these are very powerful bounds. Here's the same thing shown again. This is these bounds to W's, down quarks, up quarks, and the gluons. I showed you the values assuming F is 1 TeV. If F is bigger than 1 TeV, you see that these bounds get even stronger, but logarithmically it's not a very strong effect. And you see also the mass dependence here. Solid lines are massless and dashed lines are 200 MeV. Like particle. And finally, for the gluon case, for the magenta lines here, we needed to assume that this unknown coupling GH theta is 0. If it's not 0, you get an extra dependence on this coupling. And depending on the sign, it can strengthen the bounds or weaken the bounds, but again, the effect is not dramatic. It's reasonably smooth. And this is something that one could compute using lattice QCD. It's just that people haven't done it, but one could in principle compute this coupling on the lattice. And that's my last slide. So a couple of years ago, we have written a very long review type paper on flavor bounds on axion-like particles, and I show you a plot from this, even though this was still based on the leading order analysis. Now we have the next to leading order analysis, but we only have it for kaon decays. We don't have it for any of the other processes. But you see here, I don't know if this is readable. This is the constraints on the up sector bound and on the down sector bounds. And you see the most strongest constraint is also for the scale. So this is a few times 10 to the minus 3. This is exactly what I showed you in the table before. And you see that this kaon bound is the strongest by far until you reach the point where the alt cannot reproduce the kaon decays because it's too heavy. And then some other bounds kick in. So particular here, then you have B physics bounds, which shapes high decays and so on. But overall, I mean, flavor is incredibly rich field of constraints on these bounds, depending on where the mass is. And they go up to the mass of the D meson, of course, and then they stop. So below 5 GeV, we can have these very strong bounds. So that's it. I think I really liked working on these axion-like particles because it's kind of a very cute model that automatically gives you, for a heavy no physics scale, a very light no state with very weak couplings. You don't have to tune anything. It's just this proportionality to the inverse of the decay constant. And these are an interesting target for searches using collider data, flavor data, and also position probes. I showed you the Higgs example, a flavor example, and I also showed you G-2 as a way of also probing some poles of these axion-like particles. And basically, this flavor constraints in the range where they apply, so for relatively light axion-like particles, they give the strongest of all these particles. So thanks very much. And again.
Thank you. Questions? Yes.
Sorry, yeah. This is the equation. So basically, what you see here is the RG effects running from essentially, so F is a TeV here, so we run from 4 pi F, so 12 TeV down to, I think, 2 GeV is where we stopped, and then matched it onto the chiral Lagrangian. And you see, for instance, this is the upcoupling at the high scale compared to the upcoupling at 2 GeV. You see kind of a 10% reduction here, and then you see that all the other couplings coming in. So, you know, the upcoupling at low energy gets a piece proportional to the downcoupling at high energy, to the gluon coupling at high energy, to the W and hypercharged couplings at high energy. And yes, these are loop effects, so they can be small, okay, 4% correction. But for instance here, I don't know, the downcoupling gets a 13% contribution from the upcoupling. So, you know, you can have a model where you say, I don't want effects in K and physics, so let me set the downcoupling to 0. But then you run down and the upcoupling, because of this top loop contributions, feeds in. So I think the most important thing is that everything mixes with everything, so you cannot really, people have written papers about like photophobic models where the Alps doesn't couple to photons at all. It's impossible to implement because of this mixing. It will always generate at some level these effects. And the effects here in the flavor changing is not so small. You see 10 to the -5 here, but then a 10 to the +3. So the top contribution here is a percent type VTP-BTS. And in the standard model, if you know flavor changing effects, it's a loop factor times VTP-BTS. So basically, you can actually compete with standard model flavor changing neutral current scales. So these effects are not small at all in that sense.
I have a curiosity. You mentioned this X. This is the X17.
No. This is just X means for them means unknown loop particle.
Okay.
And the X17 is another. I mean, it could be. Okay, it could have been. But, it was 7. I forgot. Was it 17 keV or MeV? MeV. So it could be produced there.
Yes, this is what I was wondering.
In fact, we also in this very long paper I mentioned, we also question the idea whether an ALP could be the X17. But I don't know if there's still evidence for this X17 as far as I remember.
No, I don't know.
It has not been confirmed by independent measurements yet.
Yeah.
All right, so Thank you.
Thank you. I will just, okay, part of this you have already seen. We know that we have a nice tool now to look for the physics. And that's the LHC. We are happy to give it a nice time. And with this, the LHC opened a window for the search of new physics, a new window of opportunity in the TeV range, a few TeV range you can make directly discoveries. And also the LHC allows us to test very well the standard model. This is just a compilation, I think, by CMS of the standard model process. Don't bother about reading this. When I want to read this, you have to grow it a lot. This is just a production of electroweak gauge bosons with jets, 2 electroweak gauge bosons, top physics, and Higgs physics. What's the message that we have to take from the present status? Is that the experimental error in the measurement, the error in the theoretical estimate of the cross-section A and B. Basically, there is no degree of new physics in those measurements. And even if you look at the time, the energy evolution of the cross sections, you can see that everything's very well inside the standard model predictions. So that's nice. That's one nice thing. So the standard model is doing well. Then we have to, the LHC can also be used to search for new physics directly. That is, you look for a bump in the kinematical distribution, where like it was done for the discovery of the Higgs. You look for the invariant mass of the pair of photons, and you see a bump, and that this was the Higgs. You can look for that directly. That's a direct search for new physics. Or you can look indirectly. You see that you have the standard model prediction, and then your data starts to deviate. This is a bit like the situation that we had before a long time ago in the 1780s, that you have plus and minus into hydros, and the machines were increasing the center of mass energy. At some point, you see that there is a turn here, and this is an indication that you have a dizzy at a higher mass scale. So, but the direct searches up to now have failed. If you look at, for instance, this is just to illustrate what I'm going to say. If you look for SUSY particles, that's was a favorite model we looked at the LHC. You see that the bounds are in the ballpark of 1 to 2 TeV, or even more. If you look for other kind of states, you can get bounds of 3, 4 TeVs, the lower bounds for the mass of these states. So one thing that's clear is that we have no indication that we have some weak state above the electroweak scale. So and we have the total rates are in agreement with this standard model. So what we are led to is to precision measurements. That means I'm going to measure the tail of the solutions. And this, and for this, the bulk of the cross-section usually is not on the tail, it's before the tail. And when you get to the high energy part of the tail, you have to have a lot of precision, both in theory and experiments to be able to do that. So if you see something like that, just remember that's the situation in the 70s when it was a minus collisions and disease. So what we are going to do is to assume that there is a mass gap between new physics and the low energy scale. And this will basically describe the low energy scale by an EFT. The fact that we are using an EFT is that allows us to quantify this deviation from the standard model predictions, and also correlated experiments. So one choice That's what I'm going to use here, is to assume that the gauge symmetry, external model gauge symmetry is realized linearly in the EF. So what you do, these are briefly just a reminder. Gustavo has already written, you start with the standard model, then you write higher order operators expressed by mass columns. When you do the calculations for the LHC data predictions, what you do is that the matrix that you have contributions in powers of 1 over lambda. In fact, you have just even ones. Basically, dimension 6 is the first one to contribute to the LHC process, and then the corrections are dimension 8. And then when you go from the square of these cross-section ratios, you have the standard model contribution, an interference term that goes like 1 over lambda square. Then you have the square of the dimension 6 contribution, and the interference of the dimension 8 in the standard model. So, given this, let me just say what's my goal with it. My goal is to study what's the importance of this term, because sometimes you're forced to introduce dimension 6 square, and then you are introducing, you have an unknown here in your results. So my goal is to estimate how large is this in one process. Okay. Nice things about the linear realization of symmetry. You can write operators, as you know, Quick's book, and you write for the higher invariant standard model H2. And once you look at the operator, let's look at this one. This one is nice, the beta. You have contributions directly to Z W, to gamma W, to Higgs gamma Higgs gamma Z, and Higgs W. So you have correlation between the results. If you see deviation in one, if this is the correct description of the high energy physics, you should be see deviations in others. So, or flipping the coin, you can get all those data sets, the information of those reactions, and constrain them those companies. So that's the nice. Okay, so nice, but there are problems when you count the number of operators. And this you can do with the Hilbert series, and this has been done by Henry and Murayama a long time, some time ago. And you see that already at dimension 6 with just one family, you have 84 different structures. Gustavo counted 59 because 84, you count the emission conjugate as a different one. By its series. But then if you go to the dimension 8, you get a little, you are shy of 2000, which is 1000, sorry, which is a big problem. But then when you remember that you have 3 families, you get 3,000 structures at that dimension 6. What that means, you have in fact, you are going to get 2,500 universal coefficients, independent coefficients here. And then when you go to dimension 8, you get to the 44,000 structures. That's too much. So that means that you have to do some hypothesis. And hypothesis comes basically because what increases a lot the number of operators is the number of factors. So this has to do with factors. So when you do hypothesis on flavor physics, for instance, if you get not really precision data, that just means the coupling of the Z to the standard to the fermions. If you pose a very strong symmetry that's it's family independent in each generation, you get 10 operators. For boson production, boson production 200 page bosons, you have 11 operators, even with strong choices. For top physics, it's impossible to. You're going top and to impose symmetry on the top. If you relax the symmetry, you have 22. But for the Higgs physics, even with the strongest one, you have plus 18 operators. With this service, just to tell you that there is simple analysis have large number of operators, and you have large data sets. Right? to get different data, or the most data that you can, and then you use the correlations to be able to construct the patterns. Okay. So the next step, you just have to define a basis. Define a basis means operators that differ by the equation of motion or by integration by parts, they give the same as matrix elements. So they give the same physics. If you want to do an analysis, you want to fit the data, you cannot have two operators that have the same effect. So you do that, you get a basis. In the case of dimension 6, you have 59 operators. This is just one example. Okay. Let me now get to the point that I want to do. It's nice that you have an expansion, a formal expansion, I would say. And you say, look, I can do my analysis with the dimension 6 terms. And I just get interference, I do my analysis, and this is, and I don't have to deal with this, and then I'll see that if that is large or not, if this is consistent. But then there are processes that you must introduce higher order terms or do something else. For instance, if you study PP going to production of a W plus W minus pair where both W's are longitudinal, you see that the cross-section gets negative at some point in the DT distribution. So this is wrong. And this is what was expected. If you have interference of two terms, just reverse the sign of the initial coefficient of this. At some point, you get something negative if it's large enough, if the bounds are not strong. So you have to introduce the next order dimension 8 operator, but it doesn't come alone. It comes with the dimension 8 contributions. And what I want to do is to estimate the size of those dimension 8 contributions. They can be important or not, just to have an idea of their part. To do that, since there are so many dimension 8 operators, we need I did this with Tyler Corbett from Vienna, Kochar from Stonebrook, Eduardo Almeida from Bahia, and we did this analysis. Peter Heinitz, he is a postdoc in Sao Paulo, and we did this analysis, and we introduced a few dimension 8 operators. What we did was just said that we assume that new physics is universal. That means that you can write all the low energy effects in terms of those operators. That means it doesn't touch the feathers. It doesn't mean at the end that you have just bosonic operators. It means that it can be written this way. Because you use the equation of motion to go from a larger set of operators to a minimal set. When you do that, sometimes you get rid of all those operators. You still have effects. This has been taken care of by Wells and Zahn. So what we did is just analyze the metric precision data together with the data from the LHC for the production of type bosons that measure triple-H patterns. Of course, I don't want you to remember this immediately, but you have operators in dimension 6. Usually, it's the first line that enters. And when you go to dimension 8, you have their siblings. You just multiply this operator by phi diagonal phi, you have a dimension 8. That's what. And then you have new operators that appear like this one. So this is the set of operator that we consider for the analysis. And here we are using the dimension 8 basis by life. The operators that we get to modify the triple-H couplings are the dimension 6 ones, that are those 3 here. And this OBW also modifies, but it's constrained by the network precision data. And their siblings that will be multiplied by phi diagonal phi, and the new one that appears as 3. So altogether there are 11 operators. 11 multiplied. 7 with 7, 14 operators. So we are going to perform a 14 operator analysis in a very restricted case to know the effect of the dimensional operators. So we go there, write the effect in Lagrangian with the use of coefficients, and then we select our data. And then with the lateral precision data, we get the lateral observables, that's Higgs width, atomic cross-section, bunch of symmetries, ratios of cross-sections, and forward-backward symmetry from the B and the C. And also we add to that the mass of the value and the limit of the value. That's what I call my atomic precision observables. We go there, and then we have to calculate the effect of the higher order operator on this. You start doing this, you have to define your inputs, take into account the new contributions. That's basically like redefine inputs when you do the normalization. And then to order one of lambda to the fourth, basically what happens is that the Z couplings depends on 4 couplings. It's the dimension 6 plus the sibling divided by lambda squared. This is nice. You go there, you do all the machinery, and you get this. But then there were 4 dimensional operators. The fourth one is it doesn't appear in those combinations, so we have to take into account. And when you do that, you end up with the traditional oblique parameter analysis. People that are old enough to have used this time to the analysis of alpha, T, U, and delta G over G. When you do that, you notice that at least for the couplings that are Higgs to H bosons of fairness, that when the green line here is when you have just dimension 6. When I add the dimension 8 operators, I move to the blue line. As you can see, the introduction of the dimension 8 operators is mere change the limits that we have. And let's see here numerically downstairs, but it's not a big change. In a sense, the impact here is small. So we basically can say that all the couplings to fermions are these bosons to fermions are in the standard model. Why I'm doing this? Because I want to study the production of dibosons. Dibosons involve the fermion couplings. If I put the fermion couplings here, it's undoable. So what I do, I just assume that the couplings are so small that I neglect them, and then I consider just the ones that modify the triple H couplings. And if we do an analysis similar to the one that we have for the fermions, you get the modifications, you absorb them in the redefinition of the dimension 6 once, which means that we at the end of the day, you introduce one of the lambda to the 6 contribution that we are neglecting. We end up with 4 operators. We construct a chi-square. We get the data from Atlas and CMS, and then we can do the fit. How much time do I have?
3 minutes.
Okay, so that's good. So let me start as the previous case. The green line are the limits of the triple H couplings observed FB, FW, and FWW. 3 operators. 3 of those operators. That's the green line, continuous green line. If I introduce just the dimension 6 square, I get the dashed lines that you can see that are here. They are here at this line, and they are. So it serves to have FB and FW to enhance the bounds that you have. But then you have the question, what's the effect of 2 dimensional operators? when you introduce the remaining relation operator, it basically does not modify the results that you have using the dimension 6 square, and what you get is a bound on the other operator. So it's very nice in the sense that you still keep the power that you had before, but using the dimension 6 square term, but you have everything under control. This is a nice thing, and you see that when you introduce the dimension 8, some bounds get improved by a factor of 4, while others get screwed up by a factor of 20. But that's effed up. But still, the final results are nice for supergravity. You can play and say, okay, I don't want to just rescale the couplings. I can play the same game with the full, now with the full expression for all operators, keeping now without rescaling, keeping as independent every piece. When you do that and you do the fit, you still have results that are very reasonable. You don't change much the results that you have from before, meaning that everything is controlled. At least in this sector, it's under control. Yeah, and the reason is simple. The new operators don't, the bound operators on the tail, because the tail introduces foundation of the growth of the cross-section. And the growth of the cross-section introduced by dimension 8 is fine enough not to perturb whatsoever. If you have a larger growth, impact will be larger. So just to finish, LC is becoming a precision machine. I think that's Gustavo, the point of Gustavo. My point here is it's going to, if you don't have a new discovery with larger luminosity, it's going to be a nice machine for discovery, for precision, when we have 3,000 reverse femtobards. And a lot of effort, both from the experimental and the theoretical community, are going into this analysis. So in the future, we expect that those bounds that are now in the ballpark of 1 TeV. If you look at the lambda scale that you take for the Wilson coefficients of the other 1 TeV. 1 TeV, you should say, new physics should be exploding in my face. But in fact, this 1 TeV is an effective scale. This 1 TeV is the real scale that you have divided by the coupling constant of interaction. We are starting to probe now strongly interactive theories that are in the ballpark of 4 or 5 TeV. But with more precision, we will be able to also probe theories that modify the strength of the natural one. Okay, that's all I want to say. Thank you.
Detailed the question that there's this approach that people call geosmath, which basically sums up the multiple Higgs insertions. And many of the operators here that you discussed had extra pairs of Higgs.
Yeah, those.
And is that similar to your gender parameters?
Yeah, this is doing geosmath. In the sense, it's geosmath with a small thing more.
Yeah, but that's what I thought. But
yeah, for the precision later, for sure it's geosmath. It's very same, very good. But the point is that you don't need to do that. You can do you can consider that the things are not it's doable. But it's doable in a small set of data. Because with 40,000 operators, there's nothing really you can do.
And then the values you show here are always
in 1 over TeV, 1 over TeV
to the end, right?
Yeah.
For example, A of times the field strength, quadratic field strength, not this higher derivatives.
Oh, that's to think that with dimension 8 or dimension 6. In dimension 6, you can transform those operators. Those operators can be shown that are in the form that the operators that are removed. Yes, you can use the equation of motion. You end up with the fourth order operators. In dimension 8, there will be siblings of this operator. It's just put a fine square or, and in general, my class is I don't know. We are getting all the dimension 8 operators that are orthogonal, rotating, and we are in the process of doing that. Pardon?
There are some which something was the state is more ghosts.
Ghosts.
Is it possible to exclude some operators on the basis that they do some models?
Oh no, that's for sure. There are works that work for linearity and put bounds on sums, or some of the coefficients have to be positive and something like that. I've seen works looking for that. It's possible to do this, but it's not that it is good operator. The ones that I saw, they were just saying, okay, given some of the coefficients should be positive.
Production. The difference of the dimension is effect is smaller than what it is in the dimensions. Is it because of the influence of the dimension is smaller than the what it is in the dimensions?
Yeah.
So is it because of the momentum dependence of the object?
It's not that small. Yes, see, it's small in the sense that the Lewis coefficient that you need is larger than the others. That's if it doesn't,
they have the dimension 8. It doesn't change the limit on dimension 6.
No. When you have here, you see, you change a bit. Sometimes you change a bit. Look at this one. You change a bit. When you add the dimension 8, you change it. Let's say, but it's a factor of 2. It's not much. So it's okay. Now this is for the electronic. If you want to the TGC, you see that this is the same, basically the same, but sometimes depends on case by case. But it's not a big effect. We do some boxes. If I open up all the possible operators, then it's hard to see.
Great. Yes, thank you. So I will talk about the simple station that we can do to the standard model and see what happened in the phenomenology of dark matter models. So the anomaly cancellation in universal station of the standard model can always summarize or we think in terms of just 2 anomaly conditions that need to be satisfied. At the end, we end up with some set of integers after the anomaly cancellation, and these integers need to satisfy that they have 0 linearly and 0 when added in the cubic way. For example, in the secluded case station of the standard model, I don't consider here the like fermions like that have opposite charges and the anomalies are cancelled automatically, but chiral fermions, singlet chiral fermions that without loss of generality, I assume that are left-handed. In this case, we need only to add
a set of these standard model singlet fermions, each one associated with one abelian charge, and this abelian charge will satisfy the Fermi equations. So I will focus here in particular in the model with some assumptions. For example, that there is a new Higgs mechanism there. I mean that all these set of fermions are either massive through the spontaneous symmetry breaking of the Abelian symmetry or massless. But I will assume that there is no vector-like fermions involved. The symmetry breaking is given by the scalar potential here. Another assumption is that in general, we will have a set of massless fermions that will be used for several phenomenological purposes. And the other ones that are massive can be proposed as dark matter candidates. Because the integrals are not breaking, then in general we will have multi-component fermion dark matter candidates in this kind of cubes. In the case of the secured gauge symmetries, we avoid the constraint from the elixir for the set prime because this dark photon, for example, didn't couple directly to the standard model fermion. So in general, we have a wider parameter space to explore. So for a more concrete example, I will consider, in this case, a set of theories when the neutrino mass is generated through effective Dirac neutrino operators. So the idea here with this secured symmetry is that the Yukawa term for Dirac neutrino masses is forbidden because the right-handed neutrinos makes part of the set of massless fermions. So the three-level contribution is automatically forbidden. However, we need to include the singlet scalar to break the symmetry, and we can use this to try to allow this operator to a higher dimension. So in this setup, we can use, we can search for integral solutions that have repeated integers that can be identified as the right-handed neutrinos. We can have either 2 or 3 because the neutrino physics still allows for massless neutrinos. So we can start at 2. And the other ones we assume that are massive singlet chiral fermions that can be good dark matter candidates. So the constraint here is very easy to satisfy, and with the ambiguous the charge, the required charge for the scalar that break the symmetries. So to search for a specific realization, we use a mathematical setup that we actually built when we have around 2 million of these integers that satisfy these 2 conditions. With this, for example, we impose the previous phenomenological requirements. For example, we search for integral solutions that have at least 2 repeated integers, like this one, where 5 is repeated. And the other integers need to form massive fermions. So, for example, if we choose here the previous condition for dimension 1, that the scalar singlet have the same charge that the right-handed neutrino, absolute value. So we choose here these are the right-handed neutrino, this fixed the charge of the scalar field, and we can see here that we are able to find a set of integers that all the integers can be coupled to this scalar singlet. For example, these 2 can be identified as 2 singlet fermions that have a Yukawa term that will give a mass after the spontaneous symmetry breaking, and this one also. And the same happens to all these possibilities, and there are around 1,000 of them. These are the simple one.
Here, for example, we have 3 repeated integers that can be identified as 3 right-handed neutrinos, and we have a lot of possibilities. But in this case, most of them have usually multi-component dark matter particles. For example, the simple case already have 2 Dirac fermions, or 2 independent dark matter particles in one generation each one. But we can have many possibilities. For example, here we have, let's say, 3 Dirac fermions, massive 3 Dirac fermions and 2 Majorana, and some of the Dirac fermions have 2 generations, etc., etc. So in this model, in general, features multi-component fermion dark matter scenarios. So focusing in the simple case, for example, when we choose this solution, so the massless simple fermion can be identified just as 2 right-handed neutrinos, and the other 2 set of fermions will play the role of the dark matter candidates. Here, the effective operator is realized at dimension pi, and I choose this effective operator in this way, such that pi have the proper charge that need to be -5. With that, we already mentioned that in this Lagrangian, all the other fermions are massive. And for example, the -3, -2, and 1, -6 can form Yukawa couplings that, after the spontaneous breaking, give you 2 dark matter masses. So in this scenario, we have 2 dark matter candidates. Each one have this kind of annihilation processes. In order to have the proper relative density, we need to assume here that the fermions have masses larger than the corresponding dark photon. And moreover, in order to have a really relative density in the dark sector, we need to guarantee that the dark photon is unstable and decay sufficiently fast. But contrary to the usual dark photon models here, the dark photon can decay directly into neutrinos. So we have here, we don't need here really the kinetic mixing. So the constraints are much more relaxed. So in these kind of models, we don't need to worry about the constraints from the kinetic mixing. So basically, we have a dark sector that annihilates into neutrinos, and these neutrinos later on plays the role of the plasma that absorbs the annihilation of the dark matter. So the usual standard model role in the Miller scenario. Here we have one conversion processes when the dark matter candidate converts into another. So we have, for example, a region in the parameter space. Here, for example, we have the first candidate here in 1 within a range of GD masses, and we have here the second dark matter mass, and we check. We make one chi-square fit to find some solutions, and we can, for example, in fact, check that there is some region in the parameter space where we have sufficiently large mass for the second dark matter candidate. All the relative density can be explained by the lighter dark matter candidate. But we also have a specific realization where the contribution of the 2 particles is important. In this kind of scenarios, for example, without constraint from kinetic mixing, you can easily propose a huge range of dark matter masses. For example, here I will decouple the second candidate and place the gaze coupling to
upon 1. For this dark matter candidate, we can have masses in a wide range of possibilities, but also a very long range of possibilities for the dark photon mass. And without further constraints of direct detection or indirect detection. So the idea of this kind of model is give you another possibility to generate dark photons scenarios in which we have additional dark matter candidates that can be explored with a phenomenology which is different than the usual dark photon scenarios with kinetic mixing. In principle, the same game can be used for Majorana neutrino masses and missions. Here in the secluded scenario, we just have a set with our hypothesis, a set of extra heavy fermions that can play the role of the dark matter. And because of the structure of the Weinberg operator, this is already allowed by the theory. So here the kinetic mixing automatically appears as in the usual secluded scenarios. However, we can permit this with just the particle content and allow it by in a higher scale with this extra operator dimension 6 that is automatically allowed. This basically, for example, in the case of the sphetogenetic scenario, imply a new heavy particle here that when the couple generates the usual photogenic model. In this case, in general, we can have, for example, the realization of the model that involves a lot of a complicated scalar set. And again, these all particles need to have sufficiently sufficiently large number, for example, at least 5 fermions in order to cancel out the anomalies. So also features multi-component dark matter. For example, in this analysis, we end up with several thousands of specific models, with many of them with at least 3 Dirac fermion dark matter particles, around 100. So in this case, for example, this is one of the solutions with 1, 2, 3, 4, 5, 6, 8 chiral fermions. And if we choose here the chart of the fiber is no longer constrained to be 9, I can form these 3 pairs. That implies that one of the dark matter candidates has multiple generations. So it's a multi-flavor dark matter model with multi-component dark matter. So in principle, we have here 3 independent fermion dark matter particles. And in principle, we can reduce the number of dark matter particles by searching for mixing between them. And there are around 40 models, for example, with this feature, in which, in principle, we have 4 independent Dirac fermions, but 3 of them mix between them. So at the end, we have a complicated mixed sector with only one dark matter particle, because it's the lightest of this sector, and another independent one. So this model is really a model with 2 fermion dark matter particles with a very rich phenomenology. Maybe we go fast. Finally, for example, there is also the possibility to simplify the scalar sector. Sorry, it's one problem with the version that was uploaded. For the simplified, the scalar sector to have only
a set of scalar spheres. In that case, we will require additional fermions. For example, in this solution already found for this kind of realizations, the Majorana here, the particle here are chosen to be Majorana fermions after the spontaneous symmetry breaking. So there are two Majorana fermions of sharp 1. If we can choose, we will choose the scalar field to be 2. These two fermions here, this two Majorana fermion generates all the neutrino masses. And in addition, we end up with two additional dark matter candidates. So we end up here with 3 dark matter candidates, one of them Majorana fermion, and the other 2 a combination of Dylan fermions and another independent one. So in these kind of models where the scalar sector is simplified, the multiplicity of the dark matter is obviously increased. So the final idea, in my conclusion, is that we have a set of solutions that satisfy the important condition of the universal case Abelianization of the standard model, that are these two ones. And we have already explored all the solution with 12 integers and the absolute value of the integers to be around 20. This gives you a full set of solutions that can be used to found self-consistent models, just as a simple data analysis procedure. And with this full set of solutions, we have already found many new and interested phenomenological models for dark matter and neutrino physics. So,
What is the computing time for this?
1 week.
1 week.
In one for laptops.
Thank you.
The laser is working. Oh, okay. So you might be wondering why talking about confinement. Such a difficult subject. The right project from the agencies, including here ours. They say, but this guy wants to work on confinement, such a difficult problem. We should not fund it. And things like that. And another reason I'm talking about confinement is that this year is 25 years of a paper of mine that was rejected everywhere. except in one in this journal, and a well-cited paper, second most well-cited paper by Australian friends, Greg Roberts and Tony Williams. And these things now that we talked there 25 years ago, 35 years ago, are coming back. And I want to tell you how this is coming. So this is just entertain you. Everybody knows that Lagrangian and quark and Bloom degrees of freedom are not the degrees of freedom that
and observe vectors. Nevertheless, they make up the stuff observed. So this is a paper in Science that probably all of you know. This is already years old. And that is a lattice QCD calculation of the hadron masses. We have some inputs, and others are simply agreeing with known data, but there are also predictions. Okay, it's a paper in Nature, in Science. It did not be another paper in Science now from the same group that are calculating mass differences. This is much trickier, but you have to include electromagnetic interactions, and it's much more complicated. And also, you see there the agreement is very good. This is a more this is Nature, even more right. Okay. And this has to do with the axial coupling from axial coupling. And this is the PDG value, and this work is that. So these are first principles calculations from non-perturbative QCD. What did you write to? So we have the answer. QCD is the theory. So why we are not satisfied? It's essentially from the same thing that Dulce put it in this nice book here. We want to know how this happened. How from quarks and gluons you get to hadrons. So quark and gluon confinement. What is the meaning of that? First thing I think everybody accepts. The experimental fact is so far that quarks and gluons are not observed in detectors. Now, if you talk to people, confinement means one thing for some and another to others. There's no agreement how we can decide we have found confinement, proof confinement. One thing that is important is that pure Young-Mills and quench QCD are not QCD. The problem related to that is that light quarks exist. You can switch off them in your mind or in your computer, but not in nature. There is not such a thing of making an approximation to QCD by neglecting light quarks. This doesn't exist. That is another theory, which is not QCD. Quark and gluon confinement mechanisms, since the early days, many claim proofs of confinement. I have been in conferences, in talks, and proving confinement adequately some proofs. Many analogies from other fields, effective field theories, models, etc. One of the oldest is try to understand confinement in lower dimensional field theories, like QED in 2 dimensions is finding as much as possible. It's interesting to see if you can learn some features that to expect if you have a confinement, not as a mechanism, but as how to learn about confinement. We have models, things based on springs, strings, flux tubes of this kind, Wilson loops, potentials that linearly rise, null potential, dual QCD, vacuum topology, solid ones, all of them are mechanisms for confinement. I think it's fair to say that it is still an unsolved problem, but lattice QCD has brought some light on that. Some things are kind of old, and some things really recent. the first thing, flux tubes break. Okay, this image that we have here, okay, this actually happens. It's obvious, because once you have icebergs, this must happen. But what are the scales associated with that break? That is the important question. Matthias has answered that already some time, and now more recently, essentially confirmed. This is from Eboli some years ago, and here they have two static sources of color and anti-color, and then you calculate here the density of muon fields. Okay. At some distance, you don't see it there. In lattice units, translated kind of 1 Fermi, and a little bit larger, and you start separating until you get a stage where nothing is. Oh, this is going back. I already gave my talk. And you see here that at some distance, this is gone. It's nothing there. Where did it go? It was a creation of a Lyford pair here. One came here, another there, and separation. At that time of this simulation, the quark masses were quite high, the final mass was 700. But was a nice illustration of this mechanism. Okay. Now that more recent calculation 3 or 4 years ago, and then here the final masses are still a bit large and not much lower than those from that. Okay. So when you have static source, again, it's the same strategy from Mali. You fix those, and then you simulate and ask what is the distance where the string breaks. Okay. For 280 eV, the breaking occurs at 1 furthest. And for KO masses, and it has a first breaking, then you have a new flux tube, say, and it breaks at the 2 KO masses, and this gives a breaking of the order of 1.2 furthest. Okay. Now, if you have non-static sources and you have the same energy density, which is given by the string tension, it's energy per length. Okay. You see that for the pion mass, the physical pion mass, the spring breaking is less than 1/3 Fermi. Breaking happens inside the hadrons. Do not pull them out. It's impossible. Breaks already inside the protons, inside the pion, inside the protons. Can we say that there are no flux tubes in QCD? Okay. Now these are computations that are staying, but it's very indicative. Scales tell that you don't have things that you see people want. It's QCD flux. This is more recent, but it's an old subject. Goes back to 12th. Inside, it's people, more recent people here in Brazil, and has to do with some special muon field configurations that are in the schematic. You make a lattice calculation, and you sample all your muon fields, okay, and then you ask the question: what are the important configurations there that lead to this interesting non-recurvative physics. It seems that this was guessed by these people here, models, and center vortices, which are configurations in which the field associated with the phases of the people from Lattice, they have a procedure to remove these, project out these field configurations associated with the center vortices. If they simulate pure Young-Mills, where you clearly see a flux stare, pure Young-Mills stare, no doubt about it. They have seen it. It's this curve, this green curve. This has been seen since Kreutz, since the first simulations. Okay. Now, if you remove vortex, this is gone. The string, this doesn't go up. I'll have now this infinitizing. So this is the first pure Young-Mills. If you remove the center vortices, there are no fluxes. Now you have dynamical quarks there. Almost physical quarks. This is the group of alpha. If you remove the center vortices, there is no hadron mass generation. What is that? And now you have the Higgs mechanism that gives the masses of the quarks, 5 MeV, 7 MeV. And then you have the non-perturbative stuff that comes from the Travis anomaly that gives you 99%, 90% of the protons. The strength of the anomaly is explained by chiral symmetry pattern. So these light quarks, they are transformed to get kind of a heavy quark of 300 MeV. They are called restricted quarks, 3 times 300. Okay, let's go back. There's another issue here is reflection positivity. That is extremely important to understand why we don't see quarks. Okay. Problem is difficult to make a model like a bag model, like a solid model. But we are working. So this is to show that this is the quark mass function. You see here, at very low momentum, 400 MeV. This gives the proton mass. 3 times this gives the proton mass. You remove the vortices, it's gone. Nothing is left there. Okay. This is still. You have positivity violation that has to do with the spectral representation of propagators. Okay? Has to do with this thing. This is positive. Should be positive if you have a physical particle. The electron has a positive code. Because it comes from the square here. So this, if this is positive, this particle is has a massive state and is part of the Hilbert space. Okay. My time is short. Okay. There's some theory behind that. Okay. That shows that for normal field theory, this Herbert's property says that you have a pole, mass, and a function. And here it's completely empty. There's nothing there in complex plane. Now, Lattice and some continuum models, they deal with Schwinger functions, Euclidean functions. Okay? But then reflection positivity says that this has to be positive. Okay? Then, if you have something that violates that, it must have such a shape. This is the first lattice calculation showing positivity violation. This is done in San Carlos, here in the States, made by Horatiu and Teresa Mendes, and the student at that time, and they have shown that. So this is signal, is a sign of positivity violation in the Rouen property. This was done for two. More recently, this is from the Adelaide Group 2, and here they compute this function here that should be positive. This thing here should be positive, completely positive for a normal field theory. So here, untouched, ensemble, is UT, you see here positivity violation. Now, if you remove them, now vortex only, if you have only vortices, then you have a huge positivity violation. If you remove them, it's gone. You don't have any positivity violation. So we have three sources of information that center vortices are important for mass generation and confinement. And explains why we don't see quarks. Okay. In the sense that we have a spectral function that is negative, so that particle cannot propagate far. Okay, given all this, I'm using to say my students and collaborators, our task, your task, is to try to connect the dots. So we want a model understanding of this thing. So here, this is a model. We did it here, and taking a model, we have positivity violation of the spectral function. It's not very difficult to get. All this trigger Dyson stuff. To have an interaction strong enough, you get positivity violation. Now things get a little bit confusing. This is a gluon propagator calculated in perturbation theory showing complex conjugated folds. Perturbation theory, this is not triggerizing self-consistent thing. You have complex conjugated folds. This violates reflection positivity. Okay. How can you understand this? This is an artifact of the participation. What is going on? Just to mud the water a little bit more, okay. This is calculations I was involved last century. This is Yukawa model for nuclear physics. It's nucleons and mesons. Okay. Yukawa coupling here. This is an ion, and this is a gamete. You can different kinds of approximations here. Okay. Rainbow approximation is when you put the bare vectors here. But you solve this stuff all self-consistent, I think. All self-consistent. You get positivity violation, you get complex pole masses, and all that. So if you come with a model, if you come with a model and show me positivity violation and complex poles, it's not proof for me that you have proof in your model. Because I have a model that has nothing to do with QCD, with freedom, and all that. And nevertheless, perspectives, unless we gather more knowledge about some tissues, I understand that QCD is more than
You, this, can I ask a question about your slide 18? There was a statement that we could argue that some two-point function at both zeros.
The Hergott's property.
Yeah, I have no idea. I never heard this before. I'm surprised. I mean, no poles is obvious, but no zeros is very surprising that you could have control over that. Yeah, what is the idea?
The idea is that you can simply algebraically prove. This is the first thing. Just use the spectral representation. Neubert group. So if the propagator doesn't have a zero, the inverse doesn't have a zero. So that we can prove it now. This should have revealed this. First condition, resonance is that it goes.
Statement is that it doesn't have zeros in the complex plane, but the zeros could be on the real line for negative values.
No, no. You can prove that those are only for in the Gaussian space with the powers. If you have change things in the negative matrix space, then it proves.
Another question, because I don't see any answer, is concerning the last part of the talk. You had this model with nucleons and pions. Now, this is a quantum field theory in some sense.
Yeah.
So it seems to contradict your theorems.
Yeah,
so what is this model that gives all these features?
What are this sense? How if you are Heisenberg studies on the last 30 years, you have spectrum, spectral function, lattice data, everything, and it shows complex groups and positivity knowledge. Is this proof that your model?
Well, maybe it's not a unitary model. There must be some basic principle violated.
Yeah, something that is not convincing. Why is not convincing? Because I have a model that's constant truth that can show precise. Of course, doesn't fit the lattice. That's nothing to do with the lattice. But it brings this same kind of stuff there.
So thank you again for the interesting talk.
So good afternoon, everybody. So first of all, I would like to thank organizers for inviting me and for offering me to be an associate member of ICTP-SAIFR. And my talk will be completely different from Gastao talk because this is not what I will tell you is not a review, is not something important. It's just a small recent paper which I did from nothing basically, and then I got somehow excited with this and then started to tell this everywhere. So, but I'm still not sure that it's very interesting. So anyway, so I have to, but it's strange, or it was the result was strange. So I will tell you something about conformal anomaly because it has some importance for us. I will explain how we make realization in conformal semi-classical gravity. Explain what is conformal anomaly, and then this is the main part, the antisymmetric tensor field with conformal symmetry. Okay, and then we will see that there is a big difference between antisymmetric tensor field with conformal symmetry and with gauge shift, and one thing contradicts another. Then finally, we will discuss this situation when conformal symmetry controls completely the renormalization of this model, even in the case where there is no conformal symmetry. That's why I put this Cheshire cat smile of conformal symmetry to the title. And so some people didn't like it. So I got a lot of very angry bugs with this paper. Most of them failed, and I took this in big. So how it is? Let me just start with a short review of what means conformal symmetry. The first example is this. It is scalar theory with 1/6 non-minimal term. It was discovered directionally by Roger Penrose, and then in another form by Chapitov and Becker. And so this theory can be generalized to any dimension except 2, because in 2 dimensions this term gets 0 coefficient. So another example is Fernand spinor. So you have master spinor. This has to be master 2, and then it has also conformal symmetry. Okay? The transformation of the metric is fixed. So what changes is just the transformation root of the field. This theory also is of the same kind, so you can generalize it to any dimension without problem. Then let's go to another example, electromagnetic field. Electromagnetic field is also very simple in 4 dimensions, but it's difficult to generalize it to arbitrary dimension. It was done by Laser and Nicometti in 83, 84, I don't remember exactly. And recently we have found a bunch of new nests to make it, but they're all, let's say, ugly, since you lose gauge invariance, or you introduce extra fields, or you give up from locality or use. The same thing happens with the square of the Weyl tensor, which is poor gravity. This guy is conformal invariant in 4 dimensions, optimization to p dimensions. It's not straightforward. Regardless, it's possible. Another very important for us example is this. It's the so-called Panay's operator. It's 4-dimensional, 4-derivative, conformal operator, self-adjoint operator, introduced originally by Franklin and Sydney. The work is called conformal supergravity. And then actually people associated with the name of this mathematician, Panay, he published preprint in 83 and then disappeared as far as I know. So 25 years after mathematicians published this preprint as a paper, just to show the respect to this work. So those are examples. There are many other examples, but not so many, so I will mention some of them. This is our example. So this theory is conformal if you put mass equal to 0. Here, omega 1 is this expression. It's related to the Weyl tensor and to antisymmetric fields. Omega 4 is this construction with fixed coefficients. You cannot change coefficients. And omega 2, omega 3 are 4 interactions with 4 antisymmetric fields. When I did this, I thought that I invented this for the first time. Then very easily I discovered that this was actually done by Branson in 82. Then Franklin Zedek also had something equivalent regardless of this form, and of course without these interactions. And then Johann Erlanger also had something, and so on. There are many publications about this conformal model. But nobody took it from the side I did. So if we couple this antisymmetric field to fermions, you have some surprises. And the main surprise is that this theory with interaction to fermions with 0 mass is conformal invariant. And conformal invariance puts certain constraints on renormalization and on some other things. So there are a lot of publications, and I would say the big literature about antisymmetric tensor field. But usually people have in mind the gauge version of this field was introduced by an PhD called Burdman, more or less at the same time as people found first conformal scalar. And this theory has other coefficients. You can see that the coefficients are different. And this theory has no conformal empiricals. So we have one theory with gauge invariance and another theory with conformal empiricals. What this means, this expression corresponds to the situation when we have this gauge symmetry and the generators are linearly dependent. It's a classical example of this kind you can find in many books. If we go to quantize this theory, we find that it's equivalent to one single real scalar. So this theory has only 1 degree of freedom, physical degree of freedom, while conformal theory has no this restriction, and it has 6 degrees of freedom, much more. And moreover, there is a proof that this theory has no unphysical states like ghosts or tangents. And consequently, since it is a reducible representation of the Lorentz group, we can conclude that this theory has ghosts. Probably. Okay, probably has ghosts, and I would say that it really has ghosts. So we have 2 different theories with, which are basically similar because in both cases we have antisymmetric field. The question is, which one of them is worse? Which one of them is better? And the answer is, if you want a theory which is renormalizable, then this one is the unique candidate. Why is that? Because there is a theory proved by Buchbinder in 84. It is like 15 pages paper, and this proof takes 2 pages. And so this is unique paper when this was done. It proves that if your classical theory has local conformal symmetry, then one loop divergences will have the same symmetry. Okay, and on the other hand, we know that local conformal symmetry is always broken by anomaly. It was discovered by Duff and Tapper and Halter, then discussed in these famous papers and so on. So now we have the following question. How it can be that one loop divergences are conformal invariant and at the same time even at one loop you have anomaly which breaks conformal invariant. Does it mean that starting from second loop conformal theory is not invariant? This is not a trivial question as I will discuss now. So first of all, let us introduce some definitions. We can call C-type conformal symmetry is the action which is literally symmetry. We can have call N-type conformal symmetry is the action which satisfies not the identity of conformal symmetry, but at the same time is not conformal invariant. For example, this terms, topological term Gauss-Bonnet or surface term, they are not conformal invariant, still they perfectly well satisfy not the identity. Good. Now, so those are examples. In 4 dimensions, in 2 dimensions, there is no example of C-type term. And in 4 dimensions, this is Gauss-Bonnet box R. In 6 dimensions, you can have a bunch of examples. Now, okay, conformal anomaly. How you do with conformal anomaly? Let us follow Duff paper of 77. So this is not a related. You see that this can be interpreted as the trace of the energy momentum tensor of the vacuum is 0. Very good. Then at quantum level, we have gamma vacuum, which means that one loop effective action, which includes classical action, one loop corrections, which are invariant, and counterterm. Counterterm is not invariant. This gives you anomaly. What happens is that this last coefficient is ambiguous. I will comment on this in the next transformations. Now, if we have anomaly, okay, which reproduces the form of the classical action of the divergences, then we can do the following. We can, follow this trick, use this identity, this is very nice identity, which relates this another identity for local conformal symmetry and just derivative, rational derivative with respect to conformal factor in this representation. Then it's very easy to calculate anomaly because you just take n-dimensional C-squared, then it transforms like that when you go to this parameterization, and you immediately get this structure. So calculating anomaly in this representation, at least for the C term, is a trivial exercise. Very good. Now, what you can say about box R? This box R is not easy because here the first derivative is 0 because it's a surface term. So this was like a big problem noticed by Duff in his review, which was 25 years of conformal anomaly. Then we, I think we explained it in this paper with Eddie Gorber and Manuel Esre. Just noted that we found that not only in dimensional regularization there is an ambiguity which people saw before us, but also we found Paul Miller's example. And finally, we concluded that all these ambiguities are equivalent to the freedom to add R-squared to the classical action. So basically, it's not really quantum ambiguity, it's rather the possibility to define your classical action, which is not symmetric. Okay, this is all important for us today. Now, if we can make with this C and N terms, we can make classification of anomaly. It was done by Bezier, Duff, and Aishan, and then extended or repeated by Bezier and Schwimmer, a little bit corrected by Bezier himself. And based on this, people make the so-called A and C theories. It's a big business trying to show that the coefficients of C-square and Gauss-Bonnet term do not depend on the one-loop approximation. If you go to all-loop approximations, you still have the same size, and the magnitude of these coefficients should grow. This is true up to some extent, as I will explain, because if you have a broken conformal invariant starting from the second loop, then your effective action changes the beautiful structure induced by anomaly, and then basically basically you cannot even discuss the universality of these terms. You have many other terms that these terms become less important. So I will try to, as a byproduct, explain how it works. So we can integrate anomalies. This was done first time in 2 dimensions by Polyglot with the famous papers, and also in the very famous papers by Reger and Frank. The integration is quite trivial in 2 dimensions. It gives you, you have to integrate this equation in 4 dimensions. Technically, it's not difficult, and everything is based on this magic formula. This formula is very funny because if you transform each of these terms separately, you get like 5 lines of formulas. This transformation. When you sum this, then up with -2 coefficient, you have exactly a cancellation of everything, and here appears the 1/8 operator. So I asked many times mathematicians, can you make this in another way, not by primitive calculations? And they said, no, everything was done by Brunson. This is not true because in Brunson's papers there is no something similar. Let me tell you that in 6 dimensions there is similar formula. It took us, my student Fabrizio Ferreira and me, 4 years. So in 6 dimensions it's a nightmare calculus. Anyway, so if we have this formula, everything becomes extremely simple because you have this transformation for any conformal operator A, for conformal functional A, and then we find this solution and find this solution for C-square and this solution for the Gauss one. Just because it's trivial exercise, because if each of these things transform with this -4 1/8 operators. Sigma and G is the green function for the 1/8 operator, which is conformal by extension. Very good. So we can use this that R² produced box R in the anomaly, and we have this nice solution. Look at this solution. It has non-local parts and it has local part R², and the local part is ambiguous, as I told you. So this structure of anomaly-induced action holds on in any example we know. In 6 dimensions with additional fields, you can put electromagnetic field, the torsion, which is antisymmetric vector field, and so on, scalars, whatever. You always have the same structure. You have local terms, like here with torsion. You have non-local terms. Non-local terms are free of ambiguities, and local terms are ambiguous. This looks trivial, but what is interesting is that we can use this logic to analyze something related to divergence. So once again, let us think about the realization of antisymmetric tensor. We can use this book figures theorem. You can find very simplified version in our recent textbook on quantum gravity. So and see how it works. So now let me repeat a set of very well-known statements. Everybody knows this. First of all, the reversibility of the theory depends on the form of the contact terms, which you need to cancel divergence. Second, ultraviolet divergences are removed by adding local contact terms. This is what people call Weinberg theorem, but actually it was known from the early 60s. Anomaly-induced action, as I explained you, has non-local terms. Now, you mentioned that you go to 2 loop or higher loop. It's very unlikely that non-local terms in the which are generated in the subdiagrams will produce local divergences. And non-local divergences are forbidden. So basically, we're in this situation when divergences are somehow decoupled from non-local part of anomaly. Then, if we are worried about the conformal invariance of divergences at higher loops, it depends a lot on your local terms, and local terms are ambiguous. What it means? It means that if you introduce a very special fine-tuned Elot randomization scheme and kill step by step all local terms in some diagrams, then you have a chance to meet conformal divergences and beta functions and ANC theorem and whatever with high loops. If you don't do this, you have much less chances to do something like that. So let us go back to our antisymmetric field. It means that if you use this very special, let's say very special scheme of renormalization, then our antisymmetric tensor field is renormalizable in all loops, because conformal symmetry will control all divergences. The masses, even with masses, because masses is a soft symmetry breaking, which does not change the rest of the divergences. So we find a new example of all normalizable conformal field. And it was actually noticed by Abdiyev and Chizhov many years ago, but now we can put it on another basis, let's say. The most important is this relation between this term and this term. In conformal theory, it's -4. But look, there is no conformal symmetry here. You have no square root of -g. The derivatives are partial derivatives. Still, conformal symmetry, regardless it has gone, it controls the renormalization because we have a general statement, the correct statement, that the renormalization of these minimal terms, which do not vanish in flat space time, are absolutely the same in curved and flat space. And moreover, if I add here curved space, I add metric, external metric, of course, then once again, nothing changes. We still have renormalizable theory. So we have the situation when we have new conformal renormalizable theory. And this conformal renormalizable theory probably has ghosts. And if it has ghosts, then probably it's a kind of analogy of quantum gravity. Because quantum gravity also has ghosts and is renormalizable, or it has no ghosts, it's non-divergence. Again, we can calculate one of divergences in this theory and get the beta function. And we see that the sign is negative. So this theory has asymptotic free at one loop. And our continuum tells us that if we go beyond one loop, at least until 3 loops, the asymptotic freedom will be there. And moreover, we know from the papers by Gross, Wilczek, and other people in the 70s that if there is asymptotic freedom at lower loops, then at higher loops it will hold too. So we have new theory which is normalizable, which is which has strange symmetry, which may be absent by Z and is asymptotically free. So let me go to conclusions because our chat is starting to press. So,
no, not yet.
So we see that first of all, integrating conformal anomaly is an efficient way to derive effective action of vacuum, and I would say not vacuum. Then you can have this method is so nice that it can be generalized. It works in any dimension. It works in any loop order. If you have this special scheme of organization, you can add extra scalars, vectors, torsion, or even an asymmetric field. And let me say that this doesn't mean that this theory is free of problems, because first of all, you have cost, and second, I'm trying last few months to finish the analysis of anomaly, and technically I cannot do it because there are very complicated calculations, and by chance I have to do it without students. So, and I'm getting old, so I cannot make the calculations well. So yeah. So we see that moreover we have this asymmetric field, completely new situation. When you have conformal symmetry which controls completely the renormalization of the theory, and it still controls this renormalization even if you don't have metric and consequently you don't have the conformal symmetry. So and we can actually have several extensions, but discuss. Now, Abdiyev and Chizhov in this paper, which I mentioned, they discuss some applications to particle physics and cosmology, like to things like axions, to things like magnetic field generation in early universe, and CP violation and so on. But this is far beyond the scope of my knowledge and my talk. Thank you.
Thanks a lot. Yes, please. Do you have a clue about the infrared? What's the infrared?
Well, the definition of infrared may be not so simple, because, for instance, if you have free this theory in flat space, then in infrared, it's difficult to say what will happen. Okay? But if you have curved space, then this action, okay, which is these first two lines, and if you have extra fields, it will be like the second line. This section is a very good approximation to the infrared, okay, in corporate space. Until some point when, if you go to, let's say, what means infrared? So if you go to the future universe, for example, okay, once I had a paper with one student from Geneva and one in myself, and we tried to predict the end of the universe. And, okay, and we calculate actually if you take the preprint in the first version, there is a prediction that our universe will end 24,000 million years from now. We calculated this. But then, why? Because we took it too serious. We said, okay, it goes to this infrared, so we just took this section basically, and so what it would produce, it produces explosion of all matrix perturbations in future. But this doesn't happen. This is not true. Why? Because there is a cosmological constant, and in the far infrared, it starts to work like an infrared regulator. Okay, it's a big activity. I spoke to Stravinsky, who passed away a few months ago, unfortunately, and he explained this to me that I have to check this point, and we checked it. Actually, it's not true. We will not explode 24,000 years from now. Yeah, and this happens because the cosmological constant may work like infrared regulator. Okay,
but it's flat space. Just in flat space.
In flat space, yeah.
It's a stronger couple theory that.
Yeah, we will this will. Yeah, in flat space, probably you can, because there are behind these expressions, there are logarithms of box, log of box. So in because this is just a representation for log of box. Okay, a log of box is exploded in infrared. There is certain duality between infrared in ultraviolet. So I don't know from the physical side what will happen. This theory, like any others, depends on the context.
Thank you again. Which is that it's hard to do ADS CFT when you are dealing with sources that back react on the geometry. Okay, so ADS is very simple. ADS is a matrix where we have flat space in cosmic space in d-dimensions plus some radial direction. So let's draw a picture where we have flat space, and then we foliate flat space with some extra direction y, and this is what ADS is. This is ADS d-dimensional, where this is RD, and then the full thing would be ADS d plus 1 dimensional. And then we could consider ADS CFT, which is a duality between a theory of quantum gravity here that lives in this space-time, and the theory of a CFT, which is just quantum, that lives here on the bottom of this space-time when this variable y goes to 0. And ADS is basically a foliation of this boundary, as you see in the metric, where we have many copies of RD with this 1 over y square warp effect. And what do we do usually in ADS CFT? What is easy to do in ADS CFT? What's easy is to consider a bunch of probes that we insert in different points at the boundary. It's like an experiment with a light particle by sending particles from infinity. And then we let these probes move in this fixed background, which is ADS. So that's what's easy to do. It's probes. And we describe these probes moving in this fixed background, perhaps they interact. And we know how to do it in the ball, in quantum gravity. We do some scattering experiment in ADS. And we also know how to do it in the boundary. We compute correlation functions. For example, in this picture, one operator inserted at one point, another operator at another point, another operator at another point. And then we use Feynman diagrams of perturbation theory and draw nice diagrams like Gastao was doing. And then we compute this object in the dual theory, which is just a quantum mechanical theory. So that's when we have probes. The question is, suppose this operator O is huge, very, very big, means it injects a lot of energy. Then the geometry is not just ADS. The geometry itself is going to be back reactive. It's like sending a black hole. Now the operator is so big that the geometry itself is going to be deformed by this probe. It's no longer a probe. You could imagine this problem then is much harder to solve, and there's a lot we don't know how to solve, both in the CFT and in the bulk. In the CFT, similar problems appear in particle physics as well. You could ask, even in pure blue, what is the correlation function between trace of f to the n and trace of f to the n with n being huge? It's a very, very big gluonic operator. What is the correlation function between these very big gluonic operators? And it's a hard problem. So these problems are very big operators, studying very big operators in the CFT or in the bulk is an important open problem. And in principle, in the CFT at least, it's very well defined. Because in the CFT, it's not different from probes. Probes are not probes, it's the same thing, it's just an operator. In one case, the operator has dimension which is 3, and when it's a very big, it has dimension which is 3 million. Right? It's the same thing, it's just a bigger operator with bigger dimension. But in principle, it's still well defined in the quantum mechanical system we are studying. In the bulk, however, when we do quantum gravity, we need to understand the rules of the game and how to formulate it and how to understand this very big operator. So what do we know when we put some operators in ADS-CFT that start back reacting in the geometry? We know how this metric starts to be corrected. We know that this metric, which was just ADS, will receive some corrections. And the corrections, you can organize them as how close you are to the boundary. Here was empty ADS, y goes to 0 is the boundary. Then there is the next term that I'm going to write next, and then there are corrections. And the first correction here is where you what enters is the stress tensor of whatever sources you put at the boundary. So this correction is known. And then afterwards you have to solve Einstein equations to find the geometry that is inside. This first term, however, we know, and this is the stress tensor again of whatever geometry you put. Now, one thing that is remarkable, and this is what I'm going to tell today, I hate something that I could start in 20 minutes, is that in d equals 2, that is when we are doing three-dimensional gravity, this expansion actually truncates at order y squared. Not only I can write it down, but I can complete this metric and it stops. And that's of course because gravity in 3 dimensions is topologic, as we heard in the very first talk. And the answer then, let's use coordinates z and z bar to describe the boundary, which is R2 plus dy squared over y squared, plus now the components of the stress tensor, there is some holomorphic L of z times dz squared, some anti-holomorphic L bar of z bar dz bar squared. So these are the two components of the 2-dimensional stress tensor. Plus, and then there is one more term, and it stops here. L of z, L bar of z bar, dz dz bar. So this is an exact solution of Einstein equation. Plug it in Einstein equation, it solves. So it's rather remarkable that it exists, and that we know how to correct ADS whenever you have this L and L bar. They can be any holomorphic functions. But we know what they are. They are not any functions. They are the stress tensors of the boundary theory. Now, let's try to develop some intuition for what this could be. If I want to describe a very heavy operator, then this L of z, which would be related to the expectation value of T of z with some very big operator at some position, say x1, and a very big operator at some position x2. Then this expectation would be given by the following result. The stress tensor with two scalars can determine right away the dimensions. And you get the following, z minus x1 squared. There's a double pole when you reach x1. You have z minus x2 squared. Double pole if you approach x2. The residue is the dimension of this operator, which is the mass of the source that you are putting. So if this was a black hole, m would be the mass of the black hole. And then to normalize the residue correctly, I will put some x1 minus x2 squared so that the residue is just m. And so this metric here should describe the 2-point function in the CFT. What we should be describing is I have my CFT and I'll put some very big operators, one at position x1, one at position x2, and I'm describing the geometry that corresponds to this 2-point function from x1 to x2. And this becomes, if I put x1 equals 0, x2 equal to infinity, becomes just m over c squared, which is something I can always do in a CFT. So we have this L of c that you see explodes when I'm approaching the punctures. Otherwise, this is the geometry. So my geometry, any place that I'm far away here is just approximately ADS. But when I am very close to the puncture, it's not true that I can ignore this term compared to this, because there's a double pole here. Then this term can be as important as this, and the geometry is really important, and I cannot ignore that reaction. Now, this metric that Bernardo wrote is perfect, except that it's not complete. It's not complete in the following sense. It's easy to see when we use this position of the punctures. You can immediately check that now you have here the boundary. So this is the z-plane. There is an operator at 0. And then this is the holographic direction y. And you can easily see that there is a cone. And then you can trust the metric up to this cone. And this cone is the cone where y to the 4 over z bar equal to m. So this cone, okay, let me write like this. This cone is a cone where at this cone, the determinant of the metric is equal to 0. This is not a singularity, it's just a coordinate singularity. It just means that my metric is good to describe the geometry everywhere here, but here I have basically bad coordinates, and I should just pick better coordinates to pass and see what's behind the cone. Now, as we heard in the first talk, we know that all metrics in 3 dimensions, they are equal to just empty ADS. So like empty ADS, I can write it right here. There should be a change of variables that takes this metric and writes it as d capital Z, d capital Z bar, plus d capital Y squared over Y squared, where I'm introducing these capital Y's to indicate just the metric in empty ADS. So there should be a transformation from small z, small y to big Z, big Y, such that this metric, that is the metric with an insertion at 0 and infinity, becomes just empty ADS. So this exists, and it was worked out by Roberts. It's called the Roberts map. So given any L of Z and any L bar of Z bar, you have a transformation. For example, capital Z is going to become a function f of small z. Then there is an extra correction, minus y squared, some f minus y. This is a very explicit expression that once you write this capital Z like this, and the expression just has this, something very simple. You plug it in empty ADS, and you get precisely that metric there, where L of Z is what's called the Schwarzian f of Z, comma Z. This is just some third derivative of f minus second derivative over f, something very simple. So if you do this change of variable and plug this change of variable in empty ADS, you get a Nabos metric where L is the Schwarzian f. Okay? But now that you do this, now you have a complete metric. Empty ADS is complete. Except that we will have identifications. So for example, to get this L of Z, to get L of Z that is m over z squared, we have to ask what function has this Schwarzschild. I want to get L of Z to be M over Z squared. And now I ask, how do I find F such that the Schwarzschild is this? Okay, so people that are used to Schwarzschilds can do it in their head. Maybe Nathan already found the solution. And the solution is that F of Z is equal to Z to the power I times square root of M minus 1. Okay, now this is fun because you see that at the boundary, capital Z is small f. Okay, this is small f at the boundary. The boundary y is 0. So let's look just at f, which is the boundary, and let's identify and understand what happened when I went from small z to big Z, which is this z to this power. And you see that this power is very important if mass is bigger than 1 or smaller than 1. When it's bigger than 1, the square root is real. When it's smaller than 1, the square root is purely imaginary. That's precisely what we heard in the first talk. That was a range of masses where we had black holes, and another range where we had conical excesses. So if m is bigger than 1, m bigger than 1 corresponds to black holes. And let's consider this m bigger than 1 first. And now let's look at, this was the original metric, remember? There was all this metric here. This was the small z plane. And we knew what the metric was, except that there was a coordinate singularity, so we did not know what was inside with these coordinates. But we knew the boundary. There was 0 and there was infinity. And that was where the operators were. And now let's understand what happened when we went to these capital Z coordinates. Well, we get that capital Z at the boundary. Capital Z is just small z to the power I square root of m minus 1. And so let's draw, here is the small z plane. Let's draw the big Z plane here. I'm not going to draw the holographic direction, just first the Z plane. And now let's consider, for example, taking this point, say this point, and going around like this with an angle 2 pi. So that means that small z goes to small z times e to the 2 pi I. What happens to capital Z? Well, capital Z, because of this I, capital Z, will be identified with capital Z times e to the 2 pi times square root of m minus 1. In other words, going around like this in this language means going from capital Z to capital Z times e to the 2 pi square root of m minus 1. And so I can say that this circle here is identified with this circle here. And therefore, my theory is in an anomalous. I'm already identifying this circle and this upper circle. Because here, this point is the same as this point here when I go around by 2 pi. And so now this cycle that was a rotation became this cycle here. And so this inner circle and the outer circle are identified. Now what's more interesting is what happens instead if I take a point and I go in the direction of infinity. Now what's happening? Small z is starting at some point, A, and then just flowing. But this means this capital Z is rotating. Right? So I'm just blowing this small z, rescaling this small z. I'm transforming this small z. I'm making it go small z e to the lambda. And so big Z is rotating by that lambda. And so that means that I start with a point here. Or let me put the point here. And then this thing of going like this, let me draw it as a dashed line, means going around. For example, it could be this. And you just go around here in Z. Now, you see that there's no identification. I can go around as many times as I want, and I'm not in the same point. This is point A, this is point A prime, they are not the same point. And so if this is point A, and this is point A prime, if I keep growing, this A prime is not A. It just goes on and on and on and on and on and on. So what does it mean in this picture? It means in this picture that there is a cut. I need to introduce a cut. And I need to say that as I go around, I go from the first sheet to the second sheet, and then I go to the third sheet, and then I go to the fourth sheet, and then I go to the fifth sheet, and that's it. And then I can add a third dimension, which is the holographic direction, to get the final picture. So the final picture is that this picture becomes the following. Now I have capital Z and capital Y, and I have a dome, and I have another dome, and these domes are identified. If I go from inner to outer dome, it's the same. Then I have a geodesic that goes vertically from the first dome to the second dome, and there is a cut here, which is a door. So there is a three-dimensional door here. And now what I can do is take any point, it can be in the boundary or in the ball, and I just go around. And if I enter this door, I see a similar room between the two domes and so on and so forth. So there's an infinite sequence of domes, and going around this door many times means approaching one operator. Going around the door in the opposite direction means going to the other operator. And that's the geometric picture for describing heavy correlation functions. And so, just in a picture, now I have 1 minute, 0 minutes, so I'll just draw one picture. Which is now that we have this, we could ask what happens if I have a 3-point function. Because a 3-point function is much more interesting. 2-point function is uniquely determined in the CFT, there's nothing dynamical in it, it was known. This is just another way of understanding well-known geometries of black holes in terms of domes and doors. What's fun is to ask what happens for the 3-point function. And for the 3-point function, the answer is the following. That I will not go over time. I'll just say that there exists a picture for 3 points. It leads to an interesting picture where you have multiple doors and multiple chambers that you can explore. And having understood the 2 and the 3-point function in 3 dimensions, the key questions are, how do you use these solutions to learn about the boundary conditions in the ball? So that now that we know the boundary conditions, how can we go to higher dimensions and study a problem that is not topological, where we could try to set up some numerical problem, for example, for finding these geometries? That's question 1. And question 2 is then, how do we do the dual CFT computation that would reproduce the action for these classical geometries, and how do we develop techniques that allow us to see that in a CFT, which is a gravity dual, once I consider very big operators, they are effectively computing actions of classical geometries of geometry. So those are, I think, very important open problems that if we could address them, we would have a handle on quantum aspects of black holes, because even though all this is a classical limit, once I learn how to do it in the quantum theory, I will have a tool that I can study quantum corrections, one-loop corrections, two-loop corrections, everything around it, because the CFT is really a very well defined. Okay, thank you.
Any questions?
Sorry. Yeah. Did you neglect the second term y-squared?
Sorry?
Did you neglect the second term y-squared?
Now, I'm saying that you can organize the metric. Y going to 0 is the boundary. And you can organize the metric by saying this is the leading term and I'm close to the boundary. This is the next term in importance that tells me the first correction away from the boundary. And then there are more corrections.
But in order to describe the pool, we have to add y-square correction.
This is here, order y-square.
And the second one.
Here? Yeah. So what I said here was first let's analyze the topological structure of the boundary. Then I set y to 0. And then capital Z is f of small z. Then I was just analyzing there and seeing that there's an anomalous. The anomalous then going to the bulk, I need to do the full thing, and I see that that anomalous becomes 2 domes.
In this case, you consider.
Then you have to consider it. Capital Y and capital Z are just the coordinates. It's a similar thing. It's capital. There is a similar thing. Capital Y, small y plus some corrections that depend on f and f bars.
This f of z that you have, when m is larger than 1, you have this discrete scale C.
Yes.
And I mean, m is a parameter because you go from continuous to scale C.
Yeah.
To discrete one.
So when m is
determines the m.
So m is the energy. You see, it's the strength of the stress tensor. So m is directly related to how strong your source is, to the mass of your source. So m is really the mass. It's the mass.
And then when m larger than 1.
When m is larger than 1, it's a black hole. When m is smaller than 1, it's a solution that's a conical defect. It's not a solution. There's a solution which has no horizon, but it still deforms the geometry, creating a conical defect around the point. So, and indeed, we see that when if m is smaller than 1, this is just a purely imaginary number. So this tells you that you get z to a real number. And so if you have capital Z is equal to small z to a real number, then dilatations are still dilatations and rotations are still rotations. But when you do a rotation by 2 pi here, you do a rotation by another angle in capital Z, which will be 2 pi times lambda. So that's why it's a conical defect. Yeah, so the limit m to 1, there is another way of understanding this picture. If you take this picture, which is empty ADS, and apply an isometry, here you see, here I drew 2 domes that are very nice, and one is inside the other, and so on. That's not special. I could draw by conformal transformation, I can map this to 2 domes that are like this, and then there is a geodesic between the two, and there is a door here. So this picture is just a conformal transformation of that. But this picture is nice because now you can take the limit of m becoming smaller, and what happens is that when the mass goes to 1, this is the picture where the domes collide. And then when the domes are colliding, the door is disappearing because the domes are colliding. And then if m becomes smaller than 1, then the domes actually are one inside the other. And there is an intersection between the 2 domes. And this intersection defines a point here and the point on the other side. And there is a geodesic that goes from one side to the other. And this geodesic is the conical difference that travels from this point and goes around and travels to the other point. And so that's geometrically how the black hole becomes a conical defect. There was a door, you close the door, and the door became the conical defect that connects the two sides.
Somehow you map it.
The mapping now.
Not well defined at that point.
Yeah. The map, you need to define it around the point. Yeah. M equals 1 is a special one. It was also a special point in the very first talk. It was what George was calling massless black holes. It's a more symmetric point.
Okay. Thank you very much.
So the algebra homology. And like top of Ilya, it's a recent work, and I think it's interesting. But I don't understand why. It must be something. So the important part, all I will be talking about seems to be very trivial problem of extension around flat space background. So it's pure Skinner description of either supergravity around flat background or linearized Young-Mills mass operations. And the problem of finding this linearized solution can be formulated as some cohomology problem, computing some cohomology groups. And in fact, it can be formulated, moreover, it's usually formulated in terms of some pure Skinner cohomology, which is a rather unusual problem. But it could be also reduced to the cohomology of infinite-dimensional superalgebras. I will briefly review. And finally, these equations have symmetries. And so we can study basically super-Poincare group acts as supersymmetries, and we can study how solutions transform under these symmetries. And solutions form representation of these symmetries. So we can compute various, we can ask various questions about mathematical structure of this representation, and particularly we can compute like homologies of super-Poincare group with efficient in these representations. This is a very natural question to ask about mathematics. It's a very natural question, that's why it's interesting. So let me remind you that Lie algebra homology is the simplest example of what we call the RST construction in physics. So we have a Lie algebra G and its representation E. Then we introduce ghosts, which are paired naturally with generators. So they like coordinates on G, but with opposite statistics. So if it is usually the algebra, then C would be fermions. This operator is important when F has the structure constant, and so we can consider the homology complex, the chain complex, which is functions of C taking values in E. Then T acts there, and the homology is called the homology of G descriptions in E. This is the simplest, the most natural construction which belongs to larger class of constructions known as the RST homology in physics. RST transformations. So let's consider linear equations with symmetries. So, for example, let's consider Maxwell's theory. We can consider the space of solutions of Maxwell's theory, just a free Maxwell's theory, just a free electromagnetic very trivial. We can consider the space of all classical solutions, which is a linear space. We can consider the dual space, which is the space of functional linear solutions. And in particular, we can consider a subspace of dual space, which is generated by local operators. For example, operator like Fmn is a field strength of the electromagnetic field at the point 0. So these operators form representation of array algebra. And it turns out that it has non-trivial H2, non-trivial second homology group of array algebra with efficient representation of operators. And it is given by this simple expression where Fmn is field strength of Young-Mills theory. We evaluate it at point 0 in space-time. If we change the point, then it will be up to, it will be the same homology class. So the difference will be exact expression. So this is an unusual way of looking at it. I don't quite know what to make out of it, but it becomes more interesting when we pass to super Maxwell. So consider supersymmetric Maxwell's theory in 10 dimensions. And then we introduce ghosts for translations and ghosts for supersymmetries. Gamma. The field content is a gauge field and the fermions. So it turns out that this is non-trivial cycle of the super-Poincare symmetry. of the super Poincare algebra, n equals 1 of super Poincare algebra. So there is supersymmetry algebra, which consists of translations, super translations, and A is a Lorentz algebra. So that already requires computation, and this expression is only meaningful on shell because only on shell the supersymmetry generators in that dimension and means close. But I believe that it is possible to consider off-shell generalization using the deformalism, which I have not pursued. Instead, but it's a funny formula. So can we write a similar formula for supergravity? Naively, I would say that supergravity there is a B field, and I should consider H, which is TP, and subtract this E translation ghosts, and then add something for it to. So this is a cycle for Poincare algebra, but not for super Poincare. We have to get some supersymmetric completion here, but it turns out that it doesn't exist. So the right generalization is not the third cohomology group, but the second cohomology group. So again, it's something like Raymond Christoffel symbol contracted with two ghosts, and it takes values in the algebra in the super Poincare algebra. So it's not just local operators, but local operators tensor product with symmetries. So there is this non-trivial second cohomology group with these coefficients, and moreover, the full expression is very complicated. It's supersymmetric. It's all supersymmetric. It's cohomology of supersymmetry. It's very complicated expression with many terms, and I partially computed. So the main point of my talk will be to explain how to compute these things. But first, let me explain why these cohomologies appear in pure spinor formalism. So we have pure spinor formalism is very interesting. It's very unusual for physicists because it involves ghost fields. Those kind of ghosts for fermionic symmetry, so to speak. So they are bosonic. Lambdas are bosonic. They are spinors, bosonic spinors, which are pure in this sense. Lambda contracted, lambda contracted, gamma matrix is 0. So when we look at the Maxwell or Superior Mills, which are linearized tables, not different, then we construct the RST operator, which is important because of this constraint. And the solutions correspond to homology classes of this RST operator in ghost number 1. Ghost number 1 means linear inductors. Modular those which should be represented as Q of something. And in type 2 supergravity, it is a similar RST operator. Actually, there are some two which are not independent, which are kind of intertwined because this X is the same. So lambda left at the left, lambda right at the right, but X is the same. So the cohomology of this operator corresponds, it turns out, it's very non-trivial statement. Well, requires understanding why, but the cohomology of this operator really corresponds to linearized solutions of type 2 supergravity around flat space. So now I want to say that the cohomology group which we are studying is not just abstract mathematical construction, which is also interesting, but in fact, it describes an obstacle for constructing a vertex operator in such a way that it would be covariant under the action of super Poincare algebra. Let us look at it a little closer. So we can construct vertex operator for every solution. How vertex operator looks is it's an expansion in x theta lambda, and the coefficient depends on classical solution. So the coefficients could be thought of, in fact, as operators on the space of classical solutions, because for every classical solution, it prepares a corresponding vector operator, the vertex operator. So we have considered in some sense universal vertex operator, which is a tensor product of space of in the tensor identity in the tensor product of local operators with RST complex. If we pass to cosmology, then this identity is as element of operators times RST cohomology superquartary invariant, but not before we pass to cohomology. The vertex operator itself is superquartary invariant only up to few exact terms, RST exact terms. So to study this, we can introduce, and to compute the obstacle, we can introduce a complex, which is kind of a sum or direct product of the algebraic homology complex of the RST complex. It has created, you can say that creating is given by the power of the cos of Fourier algebra. Then, well, because there is gradient, there is this formalism known as spectral sequence, and we can take the identity. This is the upper picture is for Maxwell, and the lower picture is for supergravity. We can compute this high differential, which prepares an obstacle for us. So this is the cosmology class which I announced. Obtained like this, I take this universal vertex operator here, acted by high differential of the spectrum, the second differential of the spectral sequence, and it gives me this interesting expression. The computation, however, is very, very complicated. And I introduced this complex and these notions, well, at least partially in 2009 in my paper about synchronous vertex operators. But then past 14 years, and only the last year, I realized that there is a trick which allows to simplify this computation. Computation, if you do it directly, so this trick is related to the formalism of quadratic algebras, which is the algebra, which is quadratic algebra in this case, or means algebra, supergravity algebra, is the algebra is generated by letters number, which specify a constraint, freely generated by subject to this constraint. And there is similar construction of supergravity. So importantly, this G in this case would be this big algebra, infinite dimensional algebra generated by letters corresponding to covariant derivatives, and it has an ideal which vanishes on vacuum solution, and factor algebra is supersymmetry algebra. So it turns out that local operators have very natural interpretation as the homology of this complex. Now, so our total complex, so importantly, the RST homology becomes the homology of this D algebra. No more mysterious ghosts. Instead, we have infinite dimensional algebra. So lambdas would be the ghosts for the numbers. And then commutators of numbers have their own ghosts, and we have dimensional algebra. It's a so-called Cauchy property of pure spinors, which ensures that the RST homology is equal to real homology. And G over H is space-time. I told you that G over H is supersymmetry algebra. So the group I said is the space-time. See infinity without the functions. So what happens? We need to consider the homology of supersymmetry algebra in the space of functions on this set
times the representation of local operators. Turns out that this is the same, well, not literally the same, but we have to go to spectral sequence and consider, it's kind of like quasi-isomorphism, but in a filtered sense. So we have to go to spectral sequence, and the spectral sequence of this on the first page and higher pages is the same as simply the spectral sequence of the homology of G is deficient with local operators. It's kind of like Shapiro lemma type of things. So it's very much simplified. If you look at this formula, kind of this allows us together in G. I will not explain now how this is done, but it's basically the most important step here is what is called homology transfer in mathematics, and physics is called going to effective field theory or integrating out some degrees of freedom. Basically, this, if we restrict, there are both of these spaces have the same homology, and this means that you can, physically speaking, integrate out extra degrees of freedom here. Here are supersymmetry algebra active. When you integrate it out and pass to effective description, which is simpler, instead of normal action, you have what is called an infinity action. This is very typical in passing to effective theory. So this complex was normal Beresty complex, but after you integrate it out, the Beresty complex becomes corrected because the generators acting here only close up to something few exact. So this structure appears rather complicated, but in fact it collapses to the homology of G with whatever coefficients we start to consider. G is a large infinite dimensional algebra, and this yet in the computation is still complicated at this point, but fortunately it exists yet another complex, which is completely out of the blue. I don't know why it exists. It's kind of dualization in the second component. The previous complex was the differential forms, and this one is kind of in polyvectors on H invariant polyvectors. Then you have H product instead of contraction, and it turns out that physical meaning of this other complex I don't know, but it simplifies the computation because basically I don't want to just want to show what happens for young Niels or for Maxwell case. Basically, it turns out in this language it becomes obvious that the homology class is in fact the obstacle of splitting out the vacuum ideal. So it's this sigma which prevents from H being split, from G being direct sum of H and another algebra. So if you look at that supersymmetry as a cycle, which I wrote FCC plus gamma CDF. Then it is, in fact, mathematically, it's an obstacle for ideal H to be split out inside G, trivial direct sum. And it's not a priori clear why obstacle to covariance of perfect separator would be the obstacle of splitting out H inside G. But this new approach kind of verifies this and makes it almost obvious. So as open questions, I would say that it must be possible to extend this off-shell using BD formalism. I'm not sure how interesting it would be, but it must be possible. And maybe also try to see what this all means for nonlinear equations of motion of supergravity. I mean, linearized approximation around flat space is kind of boring. But nonlinear equations also, we would also consider operators and corresponding representations of all representations of work. So it was very appropriate.
Are you with your conclusions? Okay. So, any questions?
Okay. Yes.
So this means there are what this means non-covariance or versus operator, what is non-management?
Fmn Cn is not trivial. You might say that it is d of vector potential contracted with C, but vector potential does not exist. It's not gauge invariant. It's not true that Fmn Cn. You can choose vector potential by fixing gauge, but you can never choose gauge in a covariant way. It doesn't exist.
So your main result is that you always have an answer for variables, right?
I think main lesson here for me is that somehow it's very useful, at least in such toy projects, to use quadratic algebras instead of pure scalar variables. This approach was originally studied in pure scalar format, but then people kind of abandoned it. It's useful. Proposition of Fock space. Maybe there is no advantage. I would just I want to point out that there is this cosmology group. I don't think people, I asked some mathematicians, I don't think people study this. I don't think it's well known that these representations have interesting homologies and that they can be, you can import supergravity field. So the whole formula is kind of complicated. Moreover, I haven't computed it, even with my new techniques, I have not computed it exactly. Only the thing which is proportional to Lorentz generators, not the ones which multiply supersymmetry and translations. I'm not sure what, if I answer your question, I think it would be interesting to compute these expressions exactly in any format. It's a matter of applying.
Thank you again.
Thanks for